mishap. I had some issues on my end, just setting up my system and all. So yeah, I think we are ready to get started. Without wasting our time, I'm gonna dive right in. So just a bit of housekeeping. Last week I read some of the feedback, and one of it was the issue of time. So this week I'm gonna try to be mindful of our time as much as possible. Yeah, so let's get started. So we've talked about some data structures. We've started our discussion on data structures. We've talked about arrays and linked lists. So now we are going to start talking about other advanced data structures. And these data structures build upon the arrays and the linked lists. So today specifically, we are going to be talking about stacks and queues. So we're going to be looking at stacks, we're going to be looking at queues, and both of them are kind of opposite of each other. And we'll look at why they're important, how we can use them, and we solve some problems as well. So what are we going to be talking about today? We're going to be doing a recap of our memory storage, how memory is laid out. We're going to do a recap of arrays and linked lists. Talk about abstract data types. I know we talked about it last week, but I will just go over some things that will help us going forward. Then we're going to talk about stacks and queues, and then a variation of stacks and queues, which is called a DQ. Some people call it a deck. Then we move into problem solving exercises and resources. All right, so you guys have met me before. I don't think we need to go over this again. Let's dive right in. So we've talked about memory. We know how memory is structured. We know how things are stored in memory. And we know that there are two different ways we can store items in memory. The first way is to either store, so generally, when we want to store a collection of items, by collection of items, I mean things that are more than one, so that we can refer to them as a single entity. There are generally two ways you can do it. We can either store it as an array, or we can store it as a linked list. So if we store them together, that's essentially using an array. If we spread them out in memory, then we need to link them to each other. That's like a link structure. And the most basic form of a link structure is a linked list. So the reason why this is important to recap is all other data structures build upon this. Any data structure can technically be made using an array or a linked list. But as we would see, some operations are better on array and some are on linked list. So for different data structures, some data structures are more efficient when you use arrays. Some are more efficient when you use linked lists. But again, so these are the basic data structures, and all the others build up on some form of them. Yeah. Okay, so now I'm going to go to abstract data types. So I'll first start with a concept called abstraction. So abstraction is kind of something we do every day. Basically, it means when you hide details from clients so that they can focus on the essential features they need. It essentially helps us manage complexity. So let's take an example of a car. Like when you drive a car, you don't care how the engine is made. You don't care what they used to make the engine. You don't care how the gearbox works. All that is irrelevant to you. What you just care about is what the car exposes to you, which is essentially the steering wheel, the gearbox, to change the gear. I mean, if it's automatic, just the pedals. So that's essentially how abstraction is. When a data structure is made, right, data structure is usually defined using, is defined with an interface. And those interfaces define what operations can be done on that data structure. Now, the underlying details of how that data structure is made is not really important from the perspective of the client that is using it. So that's one key thing to note, and it's something we will see going forward, where we had a complex problem we need to solve, we solve it, and then we expose that interface to other people to use, and they don't really need to care about how it was solved to begin with. It's something we see everywhere, even with APIs generally. So ADTs essentially they use abstraction in a way. They define two things, essentially. What data are we trying to store? And what are the operations we can perform on this data? So essentially, it describes the interface. And the interface is what the user sees, not really how it's implemented under the hood. A key thing to note here is that the ADT says nothing about the implementation. So you can take an ADT that has been defined and implement it in any way you like. For instance, we are going to be looking at stacks. Stacks can be implemented in a myriad of ways. Some are more efficient than others. Queues can be implemented in a myriad of ways. Same thing with trees and graphs. But the key thing here is they are language neutral, in that they don't really specify what language you use. And different languages might change the names of the interfaces and implement them differently. But essentially, one thing I want to take away from this is, when we talk of data structures, the fundamental things we do with data is we store data, we retrieve data, and we perform operation on data. Those are the three key things. So when you come across a data structure, think about it like this: how does the data store information? How can I store information in this data structure? How can I retrieve information from this data structure? And what are the operations I can perform on the data structure? So if you can answer those three key things, it will really help you in like understanding how data structure works. So essentially so as we go through more advanced data structures, you should also ask yourself the following questions. Is this data structure, does it use a contiguous structure or a link structure? So some use either of them. Some are more efficient than others. Then what API or interfaces does this data structure expose? And how is data stored? How is data retrieved? And so essentially, another thing you need to also understand is what operations are efficient on data structure. Because if you look at it, any operation you can think of in data structure should be able to do it. But some operations are more efficient on some data structures than others. So by efficient, we mean O of log n and less. So usually we mean by constant time and logarithmic time. Once it's beginning to go beyond logarithmic time, it's a problem. The reason why it's a problem is these operations on data structure, they are going to be carried out repeatedly. So if to carry out an operation on data structure, you're already doing an O of n operation. When you do that repeatedly, that goes into quadratic, which is not good. So that's why it's bounded usually by log n. So in the worst case, when you do like n operations on data structure, you get n log n, which is still fine. Okay, so moving on now. So for what we've discussed so far, does anybody have any question? Are we all good? Thumbs up, thumbs down. Okay, perfect. I think we are still having a very exciting phase. I can't see any thumbs down. So we're all good. Nice. All right. So now let's delve into stacks. So now, what is it? So if you have a question, you can type it in the chat. If you don't need it to be answered right away, I'll be monitoring the chats periodically to see if anybody has any question. Yeah. So what essentially does a stack do? So a stack essentially is an abstract data type, like we said, and it supports the following operations. To push an item. Pushing an item means you add an item to the top of the collection. To pop an item, removing an item from the top of the collection. The top just gets the item at the top. It doesn't return it. It doesn't remove it from the collection. It just returns it. And then empty asks if there are any items in the collection. And size returns the size of the stack. So essentially, a stack is a last in, first out data structure. So think about a stack like a stack of plates. When you have a stack of plates, right, and you stack the plates on each other, the last plate you put on the stack is the first that gets removed. So that's essentially what the stack does. It allows you to push items to the stack. Those are the core operations, and it allows you to pop items from the stack. So the API details for different languages. So the API details may be different for different languages, but the core operations are the same. Okay, so I'm going to the chat now to some of our questions. The first question is, what do you mean when you say the operations are bounded by O of log n? Essentially, what that means is, for data structures, for any single operation on a data structure, we want that operation to be O of log n or better. So constant time and logarithmic time. That's essentially what we mean. So we don't want it to be worse than O of log n. We don't want it to be linear. We don't want it to be O of n. Reason being that when you have a data structure, the elementary operations you are doing on that data structure, when that data structure is going to be used, actually, that operation is going to be carried out repeatedly. So if we have an O of log n operation in data structure, and we do that n times, We're going to have a log n, which is okay. But once you begin to breach log n and you move into linear, by the time you do a linear operation, which is O of n times, you get n squared, which we try to avoid. So that's essentially what I mean by bounded by log n. Let me know, does that clarify your question? Okay, if I don't get any feedback, I will assume it does. Second question is, I don't understand what abstract data type means. So an abstract data type is, please can we just ensure that our mics are muted? Unless you have questions to ask. Thank you. So an abstract data type essentially is just a way of defining what a data structure does. So you can view a data structure in a way as a data type. So it defines what it does and how it stores data, but it doesn't define the underlying implementation. So for instance, a stack now is an abstract data type. Abstract data type means that it's a data type, but it's not one of the primitive data types. It's a data type that is made up of some other type of data type. So it's now abstract. So we started with primitive data types, the ints, the floats, and the chars, and then we moved up to arrays and linked lists, ways to store data. Now, we're now going on to abstract data type. Now, abstract data types contain primitive data types, but they are combined to achieve a result. Now, those results we want to achieve are what we specify by the interface. Does that clarify your question? Okay, I'll assume it does. So it said, but a linked list search operation takes O of n time, which is linear. Yes, a linked list search operation takes O of n time, which is linear. And for a linked list, searching is not one of the efficient operations on the linked list. So what I meant by the operation in data structure is you want to know the efficient operations on the data structure. So you want to know which operations you can perform efficiently. Theoretically, any data structure can perform almost any operation, but it's going to have a bad time complexity. So yeah, a linked list search operation takes O of n times, which is linear. But most times when you use a linked list, we don't search a linked list. When we want to find items, we usually search using a tree or a hash map, which gives you, so a tree gives you logarithmic time to search and a hash map gives you constant time. You rarely see someone using a linked list to search for an item now. Okay, so does that clarify the questions? Do we have any other questions going forward before I continue? Okay, perfect. So now going on to the stack, think of the stack like a stack of plates, essentially. You stack plates on top of each other and you remove the plates. The first person to get in is the last person to go out. It's kind of unfair because the first person to get should be the first person to go out, right? But that's not how a stack works. The first person to go out is kind of the last. So last in, first out. Okay. Okay. So I wasn't sharing the slides earlier, but now I think it's much better now. Yeah, last in, first out, correct. So like I said, think about it like a stack of plates, and stacks are unfair. The last inserted element is the first to get out. So we see that when we talk about queues are the opposite of these. Queues are first in, first out. So Nancy, you have a question? Go for it. Okay, I'll assume that was just you were trying to thumbs up or something. But if you have a question, you can just raise up your hand as well. I'll be monitoring the queues for anybody that has a question. Okay, so Isioma, you have a question?
Yes, good afternoon. So I just want to clarify because I heard you say something about APIs. Are you saying that the various methods or things that you can do on a particular data structure, like be under the hood, they're actually APIs, like maybe a get for an array list or something? Is that what you're saying?
Okay, so the abstract data type defines what you can do on the data structure. Now, the API is a language specific way of how that thing is done. So I give an example. For stacks, the abstract data type says we should be able to push and pop. But different languages call it different things. Python calls it append and pop. So different languages call that implementation different things. So the API is the language specific implementation of that data type. Does that clarify?
Yeah, so that's what I was trying to ask. Like, for example, now push or pop. Are you saying it's actually under the hood? It's an API.
So under the hood, it will be implemented as an API, yes.
Okay, thank you.
Yeah, but the definition of push and pop is just helping you to know what that data structure does. So anybody implementing that data structure knows what they should implement, and how they implement it is up to them. Yeah. So, okay. So now I'm going to take us on a visualization. Can you see my screen? Is it legible enough? Okay, cool. So essentially, this is, I'm just trying to, the key thing here is when you are trying to learn data structure, try and visualize data structure to help you understand what the data structure does before you even write any code. Because when you understand how it works, then it helps you build up on that. So for a stack, essentially, I'm just going to try different things. Two operations, push and pop. So when you push items to the stack, it goes on to the stack. I'm pushing another item, pushing another item, pushing another item. Now, when I pop, it takes the item at the top. It takes the item at the top, and I can push back another item. So essentially, stacks are just fundamentally, this is what they do. Now, a specific implementation of a stack could have other operations. But at its fundamental level, this is what stacks should do. They should be able to push and to be able to pop. And if you look at it closely, you discover that the core thing that's happening here is items are being inserted from one end and are being removed from that same end. And that's the key thing to note about how stacks works. They insert items at the end and remove items from that same end. So I'll go back to the slides now. Okay. So now, how are stacks implemented? I've said that the stack has an ADT, which is an abstract data type which defines the interface. But now, how are stacks usually implemented? Now, there are two ways stacks are usually implemented. Victor, you have a question? Go for it. Victor, you have a question? Okay. So there are two ways we can implement stacks. We can either implement them using arrays or we can implement them using linked lists. Now, using a linked list, we can implement it using a singly or doubly linked list as well. So how do we implement stacks using arrays? So essentially, to implement a stack using an array, we just need to add and remove items to or from the end of the array. Now, the key thing to note here is that the stack operations that we are considering, the push, the pop, and the top, remember what we said, that we want to make the operations as efficient as possible, which is at least better than log of n. So in this case, if we use an array, recall that in an array, you can add items to the end of an array easily, and you can remove items from the end of an array easily. If you are removing items from the beginning, it's problematic because you have to shift. Or if you are moving items from the middle, it's problematic. So if you add items to the end of array and remove items from the end of array, we can achieve constant time complexity for the push and the pop operations. So this is how arrays implement stacks. Now to get the top, we just check the last element in the array. We don't need to remove it. Now, for empty and size, usually how this is implemented is they keep track of this using a separate variable. So whenever they add items to the stack, they increment that variable. When they remove items from the stack, they decrement the variable. And based on that, they can tell if it's empty or not. So yeah, these are the operations on the stack. And using an array, we can actually achieve constant time complexity for all of them. So let's check the visualization here. Is this big enough, or should I make it larger? Okay. I assume we can all see. Perfect. So to implement a stack with an array, essentially, they have a variable here called top. So top is storing the next position where an item should be inserted. So yeah, we can see that the top is currently 0 because our pointer is at position 0. We don't have any item in the stack. So if I begin to push items to the stack, we see that we set start position to 1, and then we increment our pointer to index 1. So index 1 is where the next element will come in. So if I push another item to the stack, you see how the index, okay, I should make it bigger. Okay, I think I'm zooming should be, this zooming should be fine. Yeah. So essentially, I'm trying to show a visualization of a stack. And as we push items to the stack, we see that the array grows towards the end. Make the array bigger. Now you might ask, an array is static. What happens when the array gets full? Essentially, we double the array like we used to do. So yeah, that is essentially how it's implemented. When we pop, we remove it from the last index, and then we decrement that index by 1. When we pop, and when we pop, 1. So essentially, this is how stacks are implemented using arrays. Do we have any questions on this? Okay, we're good. How do we implement it using linked lists? Mano, you have a question?
Yeah, sorry. You mentioned about a scenario whereby if we have more than the fixed size, let's say we want to add more, but our array size is like needs to be expanded. So my question is, what's the cost of like O of n to like copy it into a new array that is bigger or something?
Yes. So the cost, so the cost to expand the array, to double the array, is O of n. Yes. But if you recall from our arrays lecture, when you copy the array to a new location, you double the size of the array. And because you double the size of the array, even though it's O of n, by the time you take that cost over all the inserts, over all the inserts you do into the array, it's O of 1 on average. Essentially, the O of n happens, but it doesn't happen all the time. It happens every time you need to. It happens when you are doubling the element. So if I have 2 items in my array and I want to add a 3rd item, I double the item to 4 when I copy. I'm not going to double it again till I want to add the 5th item. Then I'll double it to 8. I won't double it again till I want to add the 9th item. Then I go to 16. So because as the array gets bigger, you double it less and less and less over the entire period of time. If you average all the inserts you are doing into the array, or the adds you are doing to the array is constant. Is that clear? Okay. So that's why, yeah. So that's why the arrays lecture was very important, where we talk about dynamic arrays and how we do the copying. So when stacks use array for implementation, that's essentially what they do. They copy under the hood when it's full, and then they double it on its copy. And then the amortized complexity for pushing is still O of 1. So why would someone use a stack instead of arrays? So arrays are the fundamental data structure, right? Stacks allow you to implement certain operations on top of the array. Now, yes, you can use an array directly to work as a stack, and you can use an array as a stack, yes. In fact, in certain languages, I think like Python doesn't have a stack, a dedicated stack. It's using an array, a list for a stack. So yes, a list can be used as a stack. So you can use either of them. It doesn't matter as far as they satisfy what you want them to satisfy. So this is something I also want to take into consideration when we are talking about data structures, right? There is no rigidity that says you must use this data structure versus that data structure. They are very flexible. You can combine them in different ways. The key thing is to understand what operation you're trying to do, what's efficient on that data structure you're trying to use, and ensure that the way you're using it is in the most efficient or at least an acceptable level of efficiency. Okay. So how do we do the implementation with a linked list? So with a linked list, it's essentially the same as an array. But in this case, remember when we have a single linked list, we only have access to the head of the linked list. So we have to add and remove items from the head of the linked list. If we want to insert and remove items from the tail of the linked list, right, we need a doubly linked list. But there's no reason why you can't use a single linked list to implement this stack. There are applications for using doubly linked lists, but that's I will talk about that when we talk about DQs or decks. So let's see the visualization for that. So now we have our stack here. When we push an item to the stack, let me make it bigger so that it's better. 1 second. Yeah. So when we push an item to the stack, you notice something, right? The head is pointing to this element. When we push another item to the stack, you notice that we are inserting items at the head because we only have a pointer to the head. Now, when we push again, you see what's happening. The inserts and removes are going to take place from the head because that's where we have that's what you can access. You can't access every other element within the listen. So technically, you could store a pointer to the tail, right? Technically, you could do that. But the issue is when you take out the tail, how do you go back to the previous tail if you don't have a pointer going back? So that's why you need a W. So in this case now, let's say we had a pointer to this tail now, for instance, and wanted to remove one. We could remove one, but if we don't have a pointer back to 2, there's no way we can set the tail back to 2. So that's why we always use the head. So let's see, push. Yeah. So now when we pop, it's called that we just remove the item from the head. Pop, remove the item from the head. Pop, remove the item from the head. So yeah. So with that, we can achieve constant time complexity on all the operations of a stack using a linked list. Okay, so before we move forward, are we okay with the implementations of a linked list using an array and using a linked list? Sorry, the implementations of a stack using an array and using a linked list. Okay, so for those that are not okay, can you please ask your questions? I see some hands down. I don't want to mention names, but if you're not okay with it, just ask your questions. So in that case, I will assume we're all good with it if I don't get any questions on what we've done. Okay, I should go over it again. Which specific aspects, the arrays or the linked list? Okay, so I'm going to go over the implementation again. So with a stack, okay, the linked list, fine. So with a linked list, remember when we have a linked list, we have pointers to only the head and the tail, usually. But for a single linked list, we only have a pointer to the head. We can only insert and remove items from the head of the linked list. Now, we can append items to the tail of the linked list, but we can't remove items from the tail of the linked list because we don't have a pointer that takes us back to the previous item in a single linked list. So, meaning the only place you can insert and remove items is from the head of the linked list. And that is why when we are inserting and removing items, like I said here, we are just inserting to the head. Notice 2 goes to the head, 3 goes to the head. And then when we pop, we remove from the head. Yeah. So that is essentially what it is. Is that clear? Okay, perfect. So please ensure you understand. Okay, please ensure you understand the stack, the implementation using an array and a linked list. In one of the exercises, I will strongly encourage you in your language of choice. Take a stack, implement these operations for a stack using an array and using a linked list. Because that will really help you appreciate and understand how it works under the hood. Okay, so we'll talk about some applications of the stack. So for stacks are very useful generally. Like it's one of the most, I would say it's slightly more important than a queue, if you ask me, because a stack is very, very fundamental. Why is that? Memory management. So I'm going to take us on a trip back to how the computer structures memory. Now, when you take your program, all right, and you run your program, the computer allocates some memory for your program. And the way it does that is your program instructions are stored somewhere. This is your literal instructions that have been translated to assembly or machine code. Then your literals, like your constants, they are stored somewhere. Some static variables are stored. But the two key things I want you to understand here is stack and the heap. The stack is a special area of memory, and the heap is a special area of memory. They both start at opposite sides because they are the two of them are dynamic, meaning that they change in size. All the other ones are static. Like when you compile your code, your instruction doesn't change. Your constants don't change. The static data global variables don't change. But the memory, as a program runs, it begins to request memory from the system. Now, when it begins to request memory, it can use one of two areas of memory. One of them is the stack, one of them is the heap. Now, the stack is usually used to store local variables within a function. In that, when the program runs, it runs a function, right? That's the fundamental thing that happens. It enters, your program starts running from a specific function, right? Now, when that function is run, the stack, it opens a stack frame for that function. And that stack frame stores all the local variables for that function. Now, when that function is done, that stack frame gets popped and is lost. So you only store things that are local within a function on the stack. If you want things that are long-lived, you store them on the heap. Now, for languages like Java, for instance, Java does this for you automatically. Most languages do it for you automatically. You don't need to worry about this. Java stores it for you automatically. Primitive types are stored on the stack. Objects are stored on the heap. That's how Java does it. C++ gives you the flexibility of choosing whether I want to store it on the stack or on the heap. C does that too. But for most other languages that are high level, they do this for you automatically. So essentially, for the stack stores local variables within that function, and it's only accessible within that function. When that function is done, what's in that stack frame is gone, and it's no longer accessible. But for the heap, what you store in the heap is always accessible to you, unless you remove it from the heap. And that is essentially what garbage collection in Java does. It removes items from the heap. Python too has a way of does this garbage collection. In C++, you have to, I think with smart pointers, it can garbage collect it for you sometimes. But usually when you're using low-level languages, you have to explicitly request the heap to remove that memory for you. If not, you run into what you call a memory leak, where your computer begins to take up memory on and on and on until it's up all the memory. And then you restart the program and it's fine. So I'm going to do a demo on how the call stack works, because a stack overflow. So a stack overflow is when you put too much items on your stack, and your stack. So essentially, when your stack is full, that's a stack overflow. And usually, what happens in a stack overflow is because you are calling functions that call functions that call functions that call functions. The stack keeps getting bigger and bigger and bigger, and it gets to a point where you get to the maximum limit of the stack. So that's another key thing to note. The stack is limited in size, but the heap is unbounded. It can grow as much as possible, technically. So usually, people store a lot of items on the heap most times. So I'm going to take us on a demo of the call stack. How do we store variables on the heap? So it depends on the language you use. If you are using C or C++, you use malloc. So when you use malloc in C or C++, essentially you are telling the operating system to give you memory. But if you are using Java, you don't control it. When you create an object, when you use a new keyword in Java, it stores it on the heap automatically. JavaScript, Python, they manage memory for you. They don't expose it to you. What's the size limit of a stack? So that depends on a lot of factors. It depends on your operating system. It depends on the program language you are using. It depends on a lot of things. It's not fixed, but mostly it depends on the operating system that you're using. Yeah. So let's take this demo. I think this will make things clearer. Okay. So to make this demo, I created I'm using this tutor. They call it Python tutor, but it can visualize any language. Python, C++, Java, JavaScript. So essentially what I have here, I have a main function. And this main function, just something simple. It just adds two numbers. It makes a function call here to this function to add two numbers. And that function does that and returns the result. And then we'll print it out. Very basic stuff. So a question, static variables are stored in stacks, right? It depends on what you mean by static variables. I'm not entirely sure what you mean by static variables. Yeah. So what language is this? This is C++. Const. So consts actually they have, so again, it depends on where you define the variable. If you define the variable within a function, if you define the constant within a function, it's only going to be stored for the lifetime of the function. So you can store static variables anywhere. It depends on where you define them and how you define them. You can store them on the heap, you can store them on the stack. But global variables for optimization are stored on the heap are stored in a special area of memory. So let's go back to this slide here. You see the static variables here, static data, which are global variables. So if the operating system, or let me see now. So yeah, if the operating system is sure that some variables will not change, then it stores them in the static data area. But then you have to have defined them as global variables. If you define a constant within a function, it can be stored in the stack or on the heap, depending on how you define it. But most likely it will be stored on the stack. So different languages have different semantics about it. But I don't really want you to worry about what is stored on the stack and what is stored on the heap. It's more important to understand how the stack works and that each function creates a new stack frame. And when that function is done executing, that stack frame gets removed. So creating a new stack frame is analogous to a push. Removing the stack frame is analogous to a pop. Okay, so let's go back to our visualizer. So this is C. This is C. I use C for this because C allows you to see what is really going on under the hood. Python, Java, they do a lot of abstractions, which I'm not sure of how to turn out. But you can try it. You should probably get the same result. So this is essentially what I'm doing. Very basic function. We are adding two numbers and we're returning the answer. So let's visualize the execution. What happens when we do this? Okay, so on the left is my function and where we are in my function here on the function. On the right is what happens. Now we see we have two segments. We have the stack. We have the stack and we have the heap. Please, is this legible enough? Can everybody see this? Because this is very important. Okay, perfect. Yeah, so I'm going to be going over the function and we are going to be seeing how the stack changes. So we have our main function. What happened here? A stack frame was created for that main function. That stack frame is empty right now. Now, when we go on next, we create a variable C. Like there's a placeholder for C, but we don't know the result yet. Now, when we call add, we jump to the function add. What happens? It creates a new stack frame for add. This is essentially what is analogous to a push. So it creates a new stack frame for add, passes the variables that function needs to run in that stack frame. 1 and 2 are going to be passed into that stack frame. And you see that they're now passed. Now it does the computation and it returns. When it returns, that stack frame is popped. So when a function is called, a frame is pushed to the stack. When a function returns, a frame is popped from the stack. This is essentially how the computer keeps track of functions. And when you have a stack overflow, you are calling a function that calls a function, that calls a function, that calls a function, on and on and on and on. And that's where you hit the stack overflow. If you do recursion, we'll talk about recursion. We'll build up to recursion, but I just want you to get this idea of how functions call functions and how the stack frame is used and how stacks are used to manage the function calls. Is this clear? Perfect. Please understand this. This is very, very important for you to understand because this is foundational to recursion as well, which we'll be doing later. Somebody is having a thumbs down. Can you ask a question? Can I go over it again? Okay. So,
Yes, please go over it again.
okay, perfect. I'll go over it again. So, essentially, we understand what stacks are. Stacks generally have push and pops, but stacks are important in memory management, right? Because can I use Python or JavaScript to explain? I could try coding it in Python and see what Python does. Yeah, I could do that after this, but let me quickly get through done with this demo. I'll do that and see what Python does. But it's essentially the same concept. In Python, you're calling a function. So generally, programming languages, right? They work by calling functions. Even when you create object-oriented programs, like the constructor is a function, the method is a function. So functions are the bedrock of everything. When you create a constructor, you're calling a function, and you're passing parameters and getting a parameter back. When you call a method on an object, you're calling a function as well. Yeah. So I'll explain it, but let me go over this quickly. So we have a main function. The main function is about to execute. Every program starts from a main function. Like there's a notion of main function in any programming language you use. Now the main function starts, and a frame is put on the stack for the main function. Now, when you call another function, now on this line, we are calling another function now, and we are passing parameters to that function. When you call a function, a new frame is created for that function. And that frame is where that function does its execution. It will be created in this function here. Now you see that this A and B are passed into this function here because this function receives A and B. So that is how parameters are passed to function through the stack. When the function calls another function and it passes a parameter to that function, it does that through the stack. Now that function does a computation. In this case, we're just returning A and B. And when it returns, what happens? It's popped from the stack and the result is returned. Now, I want you to really note this now. So if I go back to my, 1 second. If I edit this code now and I say, okay, I have int useless, because I'm not using it to do anything, it's 5, for instance. I'm just creating a variable so that I can see what happens when it executes. Now, in this case, you notice something very important here. This useless is only for the lifetime of the stack. Once this stack returns, that variable is lost. That's essentially how the stack works. So someone said I should use Python and JavaScript to explain. So let me try opening a Python tab and let me just say add AB. I'll create a function to add and return A plus B. And then in my main function, I'll call add 1, 2. Let's see what happens. So it's essentially the same thing. In this case, we have the frame here. But the thing is, Python is funny because Python stores functions as objects. So I don't want to delve into that. That's why I didn't use it. So here we return, and the stack frame is popped. You see the stack frame is popped. So it's the same concept. When you create a function, you are opening a stack frame. So at what point does it create a heap? So that depends on a lot of things. Like I said, if you are using Java, for instance, Java will store an item on the heap for you automatically. Let me try and see if I can use Java to do something. So if I say int add, right? Let me see. For int add, int A, int B. If I come here and I say return A plus B, how this is correct. Int results equals to add 1, 2. So if you want to get an object, I think you need to say integer is equals to integer dot value of the string. So essentially, I'm creating an object here, integer I. I hope this syntax is correct. Let's see. Can't refer to static. Think. Cannot find symbol. Value of, is it value of? Okay, let me just use the one I know. Okay, let me just say an array list. A is equals to new array list. Let's just create an empty array list. Okay, does this work? Imports. I think I did because I didn't import. So import java dot util, I think. There's some error message here. What's it saying? Might be overloaded. Okay, let me see. Try again. Okay, there we go. Perfect. So we have the same thing in Java here, but I'm gonna make it a bit bigger. Okay. So now for Java, it's actually the same thing. We have a mainframe here where we call add for the results. It says create a new frame here, and it does the computation and pops up that frame when it's done. Same concept. Now, when you create a new array list, it says create it on the heap here. So this is an object and it's on the heap. But I don't know why it's not showing it as being on heap. Yeah. So does that clarify? Does anybody still have any questions on this? Perfect. So now we can move on. Yeah, perfect. Okay, so going back here. So I still have a couple of demos I wanted to run just for us to really understand it because it's important. So in this case, what I'm doing here is also is the same thing. But here, I have a function that adds 3 numbers. But in the function that adds 3 numbers, I'm calling a function that adds 2 numbers. So I'm calling a function that calls a function. So let's see what happens. So as usual, we have our mainframe. Now, we see that a new stack has been created for the function call to add 3 numbers. Now we continue. When we call the add to, it creates a new stack. So you can see this chain of the stacks going on. So it's important for it to use a stack because it needs to ensure that it can return from the most recent function to the previous one. Now, if I continue now, we do the computation to add the 2 numbers, and the result is returned, and it goes back to the previous stack. That previous stack returns and goes back to the main stack. So threading is a different concept entirely. It's totally different. It's not related to stacks here. No. So someone says, so basically non-primitive types are stored on the heap and a pointer to the memory address on the heap is stored on the stack, right? Yes. Generally, that's what you want to do. Yes. Java does that for you automatically. That's what Java does essentially, yes. It stores the main item on the heap and stores the pointer to that item on the stack, yes. So when your stack goes out of scope and no other item is pointing to the item on the heap, that's when garbage collection runs. Yeah. So does it mean recursion runs on stack? Yes. So recursion is essentially using a stack. Yes. What I'm doing is similar to recursion. It's just as in recursion, you are calling the same function instead of calling another function. But I want you to understand the process of calling another function first. It now makes it easier when a function is calling itself. Okay. So this is essentially how it works. Now we've done it with two functions. Perfect. So now let's see what happens with three functions. I think this is with more functions. Yeah. So now the same thing. I want to add four numbers here. But instead of adding four numbers directly, I'm calling a function that has three numbers and then calling a function that has two numbers. Cool. So let's start. Let's see what happens. So nothing interesting here. We create a stack for the add four, for the function that calls four numbers. We create a stack, push an item to this, push a frame to the stack, store the variables we need there, start executing. Now, this function calls add three numbers, creates another frame, a stack frame, pushes all the variables it needs there. That start executing. Notice that those other functions, they are still executing, but they are there, like they are in the stack. They are not yet, they're not yet returned. They're still executing. Then we add two numbers. We see that we now add two numbers to the stack. So in a Udwak, I'll give you a chance to speak. I just want to finish the statement I want to make. So in a big program, when you are running a large program, the stack grows like that a lot. Because you essentially now you have like, it's just one chain. But in a big program, you have a lot of programs calling the stack. So the stack can grow very big. And when the stack grows too big, that's why you have the stack overflow. Udwak, go for it. Okay, I'll assume you made a mistake. If you have a question, please raise your hand. So that is essentially how it works. And then when we are returning, we begin to pop off items. When we return, we pop off that frame back to the previous one. Pop up that frame back to the previous one. Pop back to the previous, and then we are done. So if you try and visualize how functions run, the stack grows and shrinks as a function call is made and returned. Isioma, you have a question, go for it.
Thank you. So you talked about this Stack Overflow, and essentially this demo you're doing now, it just reminds me of like something that I've worked on. So I don't know, should a developer be concerned about this Stack Overflow, right? What happens, like what are the dangers that occurs when you have a Stack Overflow, and then how can you avoid it? Because like you mentioned rightly, many times programs have functions that call functions and it's a chain like that. So what are the guidelines? Are there guidelines to doing that? Or what should a person have in mind when you're implementing functions that way?
Okay, good. So to address your question directly, the best way to catch this type of issue is to test. So that's why unit tests are very important. Usually for most languages, like most higher level languages, they give you mechanisms to detect this. There are a lot of static analyzers you can run during your test that can detect things like this. But for some languages like C, C++, you have to get it right. I mean, the test will try as much as possible, but you could crash the program, yes, if you don't program it properly. The program could crash. And it becomes more nuanced when it works during test but doesn't work during production, because maybe the inputs you use during test were not the type of inputs that came during production. And then the inputs that came during production began to cause like the stack to overflow. So yeah, you can try to eliminate it as much as possible using tests, but ultimately it can happen, especially when you're using lower level languages like C, C++. Yeah. But with Java, Python, they usually will catch it for you before you run into this kind of issue. Yeah. So there are different categories of the problem. If the problem is due to like a coding error, you can catch that compiler time. The compiler will catch it for you. But if it's a runtime error, then it's going to be caught at runtime. And if it's due to a certain type of input, then the program is just going to crash in production, and then you have to debug to see what happened and make your change to handle that. But yeah, testing is the way forward to catch this. Okay. Does anybody have any other question? I'm going to move forward now. Okay, let's move forward. So now we see how this call stack works, and we see how a stack is very important in the system. So this tells us that stacks are super important. I can say after arrays and linked lists, stacks are like the next important data structure. But an array can be used as a stack, technically, if you look at it. So yeah. So another application for stacks is recursion. Now, recursion is something that a lot of people fear because it looks very complicated. But essentially, what it does is what we just did, except that instead of you calling another function, the function is calling itself. Now, the same function is calling itself, but the function is running different instances of itself. So think of it like in object-oriented programming, think of it like, the class is the template for the class is the template for objects. And then when you create different objects from that class, they share the same template, but they are different objects. So you can think of the function definition and the function execution like that. You have a function defined. When you run a function once, an instance of that function is created that runs in a stack frame, in quotes. When you call that function again, another instance is created. So that's how the functions have been differentiated on the stack. But I'll go through a demo so that we can understand it more. So recursion is very important. Why is recursion important? So if you look at an array, for instance, right? If you look at an array, for instance, if you remove an item from the array, you have an array that was once smaller than the previous array you had, which is still an array. So if you keep removing items from the array, you have a smaller array, and a smaller array, and a smaller array. So you have one element in the array. So it's very important in that case. If you take a linked list, if you remove a node from the linked list, you have a smaller linked list. This pattern translates to a lot of things. If you have a tree structure, we'll talk about trees. If you remove a node from a tree, you have a smaller tree. Or you have two smaller trees, depending on how you do it. If you have a graph structure, if you remove a node from a graph, you have a smaller graph. So that thinking helps you to see that, okay, things can be done recursively. So typically how you do recursion is when a function calls itself. So it's the same function that is running, but it has different stack frames. So let's see a demo on that. So this function here, this example is calculating the factorial of a number. And the factorial of the number is multiplying the number by 1 less than the current number till we get to 1. So like factorial of 5 will be 5 times 4 times 3 times 2 times 1. Now, I could do this in a loop and just create a variable to loop from 5 to 1 and multiply them together. But I could also do it recursively, thinking recursively. Now, if you look at it, right, when you have a factorial of 5, right, the factorial of 5 is equals to 5 times the factorial of 4, if you think about it. The factorial of 4 is equals to 4 times the factorial of 3. So if you keep going, you get to 1. Now we'll talk more about recursion later, but I just want I want us to understand the idea of how stacks help us achieve this. So let's see what will happen here. Now let's execute this function. Let me start the animation. Oh, sorry, no. What's happened? So we start main, and then we call factorial 5. It creates a stack frame for factorial. Notice that n is equals to n here is 5. Now what happens? This is the base case. The base case is, so when we have recursion going on, we have to stop at some point, right? That is your base case. If you have an array of 10 items, if you remove one item from the array, you have an array of 9 items. If you keep removing an item from the array, you get to an array of 1 item, and that is your base case. Because if you remove an array of 1 item, you have nothing. So the base case is very important. If not, you get a stack overflow. That's essentially what happens in a stack overflow sometimes when you don't have a base case. It keeps going forever. Now, the base case is not hit because n is not equal to 1. But now, we are making a call to the factorial of 4. Notice that it creates a new stack frame for the same function. Now, the stack frame for this factorial function here is entirely different from the stack frame from the factorial up here. They don't, in fact, you can think about it that they don't know about each other. Just like when you have 2 different objects of the same class. So now we are in factorial of 4. Factorial of 5, you can think of it as being paused. It's waiting for the factorial of 4 to complete. Now we keep running. It hasn't hit the base case yet because n is not less than or equal to 1. We come here. Now, what is the factorial of 4? Now, we'll talk more about this in recursion, but I want us to understand the idea. At this point, you can think of this stack frame as operating on its own. You can forget that we're trying to compute the factorial of 5. The question here is, what is the factorial of 4? Now, to get the factorial of 4, We know that if we take 4 and multiply it by the factorial of 3, we'll get our answer. So that's essentially what this recursive function is doing. It opens another stack. Now, this function is trying to compute the factorial of 3. This function is unaware of the previous function. In fact, we can look at it as being independent, as if we're trying to compute the factorial of 3. Now, the factorial of 3, same thing, is 3 times the factorial of 2. The factorial of 2 is 2 times the factorial of 1. You see, the call chain is going. Now, if we don't have something to stop this, the stack will keep growing forever. Now, when we get to factorial of 1, that's our base case in this case. We know that this is our base case, and this is where we now return. We return 1. Now, that returns 1. This function is done. It doesn't know that any function called it. Back to the previous function. Right? That returns back to the previous function. That returns back to the previous function and back to the previous function. So the same function called multiple times opens different stack frames that are different based on the input you're passing. And essentially hit a base case and that returns back up. So this is how a stack helps us do recursion. Is this clear? Okay. It can be tough to wrap your head around recursion, especially if you are not used to thinking about things in that way. But essentially, you can think of recursion as a function calling a function, except that in recursion, the function is calling itself. So when a function is calling itself like that, right? If you are passing the same parameters to that function calling itself, that function will keep calling itself again and again and again. So you need to modify the parameters to pass it to the function, which is usually like reducing your problem size, like making the array smaller, making the linked list smaller, making the tree smaller, making the graph smaller, making the number smaller, whatever, until you get to a base case that can be solved. And then that base case gets solved. So you can think about it like, okay, if we have, let's say I need 1 million naira, right? For instance, we talk about this in recursion. Let's get back on track. So back to stacks. So good. So this helps us achieve, the stack helps us achieve recursion. Helps us in recursion. So you can see that stacks are very important. And stacks are unfair because it's not fair that the last person to get in, the first person to get out. But we can see that it helps us achieve a lot of things. Other stack operations, undo mechanism in text editors. So think about when you are undoing something. You do something and you want to undo it. Essentially, it's like a stack. So everything you are done is being tracked on a stack. When you undo, you just remove it back and track back. When you want to match braces or brackets in compilers, you use stacks. We'll talk about an example of that. Then another core application is depth first search in trees and graphs. That's why it's important to understand this structure. Because it comes up, in fact, stacks and queues are the bread and butter of a lot of algorithms. You cannot do without not understanding them, especially depth first search and breadth first search. We'll talk about them in graphs. Okay, so now there are different types of stack. I talked about the system stack, the one we saw that grows and shrinks as functions get called. Now, the key thing here is it's limited in space and it's used to track functions, as I said. Now, there's another type of stack, which is the one you create in your program, the user created stack. Now, that user created stack is stored on the heap. So I take this back. It can be stored in the stack or the heap, but usually you want to store it in the heap. So I know it can be a bit confusing storing a stack in a stack, but yeah, if you create a stack, you can store it on the system stack frame. But the problem is that stack you created will be lost when your function is done executing. So usually, whenever you want to create things that persist functions, you create them on the heap. So that user created stack is unlimited in space, but they work in a similar way. Now, so the key thing here is when the system stack is limited due to a number of recursive calls, you can use a user created stack to alleviate that. And one thing to also understand is every recursive algorithm can be written in an iterative way using stacks, using a user created stack. Okay, So what are the time complexities of stack operations? Push is constant time because you are adding from an end and removing from an end. And because you can access that end instantaneously, it's constant time. Pop is the same thing. Top, same thing. Everything is the same thing. Now, search in a stack is O of n. So this tells us that whenever we want a data structure that allows us to search for things easily, we shouldn't be using a stack. Excuse me. Removing from anywhere is O of n. So if you have a data structure that you want to be removing from things easily, don't use a stack. So the stack is good for pushing and popping, essentially. It does it and it does it well. Now, so you can see that the stack does these operations well and does some operations poorly. So this some of the trade-offs we see between data structures. Some data structures do something well, they do others poorly, or some do everything not too bad, but not very well. We'll see that as we go forward. Okay, so we're done with stacks. Questions before we move to queues. Which would be more efficient, reversing an array using two-pointer method or using a stack? Generally, when you use a stack, it's less efficient because you're adding more space. If you can do everything within a single function stack frame, that's the best scenario, because in that case, you are not eating up system resources by popping up a stack frame, because stack frames are expensive, they're not cheap, because you need to create a stack frame, pass functions, do some other groundwork, and then run it. So if you could choose between iterative, if you can always choose between not using a stack, don't use a stack. But the reality is some problems cannot be solved without using a stack. So in that case, we take extra space. And that extra space is of the order of the depth of the stack, which is O of n in this case. So for the factorial problem we did, it's O of n because we had 5 stack frames, because because of the n, because n was 5. So yeah, that's where we start having extra space when we add items to the stack. So is that clear before we move to queues? Very important. Please make sure you understand this. Isioma, go for your question.
Okay, so from the class we had last week, right, Mr. Our tutor told us about, like, many times you have to, like, time complexity and space complexity are two sides of the same coin, and many times there's usually a trade-off. There has to be a trade-off between one of them. And I think it was either you or him that said these days it's easy, it's not a very difficult feat to get space, but people usually go for time complexity, right?
Yes.
So
yes.
like, considering that now, so reversing with a stack may consume more space, but how about in terms of the time? Will it be faster to reverse an array with a stack than using a two-pointer?
So if you reverse an array using a stack, you cannot get a better time complexity than O of n to reverse an array. So in this case, we are using extra space unnecessarily. Now, if you are using extra space and you are reducing your time complexity, then that's a very feasible one. But if you are using extra space and you still have the same time complexity, then there's no reason why you should use extra space. Yeah. So
But I mean, like, pushing and popping have a constant time complexity, which is essentially what you'll be doing, like taking out of an array, pushing into a stack, then popping out of the stack would reverse an array.
yes, exactly, yes. But there's no reason to create an extra stack when you could do that on the array itself by swapping items in the array. You see the thing? It's correct, it works, but it's not efficient because you are using extra space for no reason in that case. That's why reversing an item using a stack, reversing using a stack is not really efficient. If you want to reverse, there are easier ways to reverse on the array directly without using extra space. Extra space is only justified, usually only justified when you are reducing time complexity. So
Okay.
if I need to use
Same.
if I need to use extra space to reduce an O of n squared to an O of n log n, that's justified. If I need to use extra space to reduce an O of n log n to an O of n, usually that's justified. But that might be debatable depending on the extra space you are using. But generally, space is cheaper than time. Generally, time is very expensive. But it all depends on what you're optimizing for. But in most things I've seen, people don't mind storing things as much as possible. Space is abundant. Hard disks are very cheap. RAM is cheap. But the CPUs are not moving faster. So the question, is there any data structure that uses O of log n or less for searching? That seems to be constant of O of n for data structure, excluding sorted arrays. So if you want to search for an item, the only way you can achieve O of log n, right, is, so there are data structures that do that. Like a hash map, a hash table. We talk about hash tables. Can do it for you in O of 1. The hash tables can search in O of 1. So when you are searching, you are trying to find an item, right? In that case, a hash table can do it for you in O of 1. You can get O of log n using binary search. But for you to use binary search, it has to be sorted to begin with. So that's one thing you need to consider. Binary search only works if the collection is sorted. Now, you can also use trees. If you can use some form of trees to get O of log n for searching. Yes. But we'll talk about trees later. Okay, so before I move to queues, any other questions? I am that OG. You have your hands raised. Yep, go for it.
Okay, yeah. So I just wanted to ask, based on the question that the previous person asked, using stacks to reverse a word. So pushing and popping is of 1, right?
Mhm.
But I don't know the process of pushing, for every character on that word, and also popping.
Mhm.
I think that should be O of n. So
Mhm.
yeah, so I don't know, but I think that might be the reason why using a stack against 2 pointer is still not efficient, because I think the processing, the runtime complexity is actually the same.
Yes, the time complexity is the same. The issue is the extra space you are using.
Yes, for stack.
Yeah, for stack, yes. But if you can do it without using extra space, I guess it's also valid. So what I mean without using extra space means when you take an item from the original collection, you are removing it from the collection and you are putting it into the stack. So you're not storing it twice, both in that collection and in the stack. Yeah.
Okay.
Okay, so I'll be moving on to queues now. So queues are essentially the opposite of stacks. Stacks are unfair, queues are fair. Queues support a couple of operations. Enqueue and dequeue. Those are the core operations. There are other operations there, but those are the 2 core operations, enqueue and dequeue. Enqueue means you add to the back of the collection. Dequeue means you remove from the front of the collection. Now, this is what the convention says, but it doesn't really matter which side you add or remove from, as far as you are removing from opposite sides. You could add to the back and remove from the front, add to the front, remove from the back. Doesn't matter. Just be consistent on which part you follow. Even for the stack, so it doesn't really matter which side you go for. From the front, from the back, as far as it's the same side you're adding and removing from. For the queue, you also add and remove from opposite sides. So these other operations are, so the 2 core operations are enqueue and dequeue. Languages call it differently. Some languages will say append left, pop left. Some will say offer, pull. But the thing is, these are the alpha data types. They may call it differently. So depending on the language, you have to find which one, which ADT is used, which implementation your language uses, and what the APIs for your language are. So a queue, think of people on the line at a teller. The first person that gets to the line in the bank is the first person that gets answered. So queues are fair. That's the key thing here. First inserted element is the first to get out. First in, first out. So let's look at the visualization of queues. So same visualization, but now we switch to queues. So in this case, we have a queue. We're in queue. We enqueue items to the queue. You see that items are added to the back of the queue. Or in this case, from the front. They're added in the front. However you look at it, doesn't matter as far as the opposite sides. When you dequeue, you see it removes the item from the opposite end. Enqueue, dequeue, enqueue, dequeue, 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 dequeue. Yeah. So essentially, this is what queues are. This is what they are for. These are the operations they do best. Enqueue and dequeue. All right, so let's go back to what we're doing here. So again, a queue is just an entity. It's an abstract data type that defines the interface. So now, how do we implement queues? What are the ways we implement queues? Same like stacks, we could use different ways. We could use arrays or we could use linked lists. Now, with the queues, right, we could use an array, we could use a linked list. It doesn't really matter. So for the arrays, how do we do the arrays? With the array implementation, it's a little bit tricky. Now, for an array, we can easily add items to the end of the array. So we add items to the end of the array. If we add to the end, because it's a queue, we have to remove from the front. But the problem is if we remove from the front and we have to shift all the other elements, that's not good because that will become O of n. So the key thing here is when you move from the front, don't shift all the other elements. Just take off that element you removed. But there's a catch. That leaves you with holes in the front of the array, right? And that means our array somehow has to wrap around till it's full. I'll explain in an illustration. Okay. So we have a queue here, right? In this case, we have the head and the tail. Notice in the stack we needed one because we were just adding and removing from one end. In the queue now we need two because we're adding from one end and removing from the other, or adding to the other and removing from one. Now, the head pointer is pointing to the head of the queue, and tail pointer is pointing to the tail of the queue. So now let's add an item to the queue. Let's add one. Notice the tail has increased. The tail is growing, but the head is still pointing to the head of the queue. Let's add two. We've added to the tail. 3, 4, 5, 6. Now, this is the problem now. Now, if we dequeue, we have to dequeue from the head, right? But traditionally, when we use an array and remove items from the beginning of the array, we will run into a problem of having to resize the array. But the trick is in the queue, we don't do that. So when we dequeue, notice that we didn't move any item from the beginning of the array to the beginning of the array. The hole is there. You can see that the hole is there. You can see that the hole is there. Now, the problem with this is these are holes here. So if the queue, let me just add items to the queue till it gets full. I'm going to make the animation speed faster now so that I can just quickly add items to the queue. I hope this illustration does it though. Now, notice something. We are at the end of the array, right? So ideally, the queue should be full. But we have some holes in the beginning. So now, when we add items to the queue, we want this to wrap around here. Because these holes are not being used. It's essentially a waste of space if we don't reuse these holes to make sure they are filled up. Because we could go ahead and say, okay, once it's full, just keep doubling. But the problem is that if we keep doing that, the queue will just keep growing infinitely. It will never it will just keep growing infinitely. So a more efficient way is for us to now. So let's say we want to enqueue, say n. Let's say we want to enqueue 11. You see, it goes back to the beginning of the array. So enqueue 11 because the array is not yet full. So that's the key thing to note when an queue is used, an array is used to implement a queue. It needs to wrap around. Sometimes they call it like a circular queue. It needs to wrap around during the implementation. So let me put 3 now. 20, 24, and now we are full. Are we full yet? Yeah, we are full. At this point, the queue is full. So, but the key thing to notice, so at this point now, the queue is full, and we can double. We can now double it. We can take the array, double it, and rearrange it better. And it doesn't really matter what is what, as far as we keep track of the head and the tail pointers. I know this might be a bit confusing, but yeah, this is just how you implement it with a queue. Any questions? Okay. So I assume we are all good with this. Okay. So that's the key with implementing with it. Isioma, you have a question. Go for it. You have a question?
My screen, but there was still a hole at position 3 on the queue. That's
I think this has to do with how they implemented it. All right. But ideally, this hole should be filled up.
okay.
Yeah.
So question I was going to ask is so we have a queue or an array, right? That you added, and then we started removing. Before continuing to add, can we add to fill up the holes before adding more elements? I don't know if that makes sense.
I get your question, and it's a very good question. Because so essentially what you are saying is if I have this and I say I enqueue these items, right? Now, if I want to dequeue, now I have a hole here. You are saying if I enqueue, I should use this hole first, right?
Yes, exactly.
But the problem is if you use that hole here, the problem is if you put if you use that hole first, the problem is that item you added will be cheating because it will jump to the head of the queue. You see the problem?
Oh yeah.
It will jump to the head of the queue. So if you want the item to bypass the head of the queue, you could do that. But then that invalidates how the queue works.
Okay.
So that item is essentially cheating because if I do 4, so if I say, okay, let me clear it and say, okay, so I have 1, 2, 3. Now, if I dequeue, I should get 1. So if I add 4 now, right? If I add 4 to the beginning, when I dequeue, instead of getting 2, I'll get 4. You see the problem? So that's why you have to be consistent.
So what then is the concept of a circular queue? That too would be cheating.
No, because so a circular queue. Okay, so I think I get your problem, your confusion now. So when you add items to the queue, you have a head and a tail pointer. The head moves as you remove items from the queue.
Okay.
So if you add items back to the queue, right? Okay, I see I see your point. We keep track of the head, but the problem is that this item we've added to the queue. When do we now take them out if we keep moving the head forward? That means we are now cheating against them because they are going to the back of the queue. Because we first have to take away everybody here before we take them. You see the problem? So if you add it to the beginning of the queue, you are going to mess up the order of the queue. So you need to be consistent with the side you add on and be consistent with the side you remove on. Now, when the side you add on is full, you can wrap around to the beginning. But because you are keeping track of the head of the queue, you're good. You're not going to remove from here. You're going to remove from where the head is. See, the head wraps around again, and you continue.
All right.
Okay. Is it not better we implement using an array list? I'm not sure I get this question. So implementing using an array list is essentially the same thing as an array. So we are implementing using a dynamic array in that case, which is essentially the same thing as implementing with an array, except that we don't need to handle the resizing. So I think by your question, you are saying when it gets full, instead of wrapping around, we should double it, right? Yes, that would work. But the problem is that that is very inefficient because you are leaving holes that you will never use again. So you consume space that are never going to be used because those space will never get used again, and they will not get garbage collected or they will not get reassigned because they've been allocated, but they are just empty. So in that case, if you have a queue so the problem with that is your queue grows not with the number of items in the queue, but with the number of NQs and DQs you make on the queue. If that makes sense. So if I have like, let me see now, for this. So the problem now is you are saying when the queue is full, right? We should not have to resize. We should keep adding. The problem is we'll keep going forward. So for every DQ I do, for every next NQ, I go forward. Let me just fill up this and try to illustrate my point. Now, when we are here, instead of going forward, we double the array. Now, this space is never going to get used. It's just going to be wasted. And if we keep dequeuing, right, and then queuing, we just keep growing it infinitely. Yeah. So it means if we have too many DQs like this, and we get here, right, instead of using all this, we create another one. And for each NQ and DQ we do, the queue grows. So it's growing with the order of the NQs and DQs you are doing, rather than the order of the number of items in the queue. So that's why it's more efficient to wrap around than just going forward. Is it because shifting is expensive? That's why we wrap around? Yes, shifting is expensive. Ideally, we want to shift it, but shifting is expensive. Shifting will cost O of n, and we are trying to achieve all the operations in O of log n at worst. So basically, we are keeping track. We are tracking the head and tail index of the array and updating the indexes if we push up. Yes, if we NQ and DQ in this case, yes. Wouldn't it be more efficient to use linked list with queue since unused memory will be garbage collected? So I would say it's easier to use linked list with queues. People will generally tell you that linked lists are more efficient with queues, but that's not entirely correct. Either of them can be efficient. It's just that one is harder to implement than the other. And the array has its advantages because of caching. So unused memory will be garbage collected. So in that case, right, if you are wrapping around, you will not have unused memory. The only time you have unused memory when you are using an array is if you don't wrap around and you keep growing the queue. Okay, so do we have any other questions? How do we wrap around? We go back to the beginning. Essentially, you use modulo. So if you modulo the length of your array with your position, you will wrap around. Yeah. So modulo is used to just wrap around. So the front is wrapped, the back is wrapped. You use modulo to wrap around. Okay. I'm gonna move. But if you wrap around, aren't you limited by the amount of items you can store in the queue? Yes. And that is what we want. We want the queue to be limited by the number of items we store in the queue, not by the number of operations we make on the queue. And if the queue gets filled up with an array, then we have to double, as usual. So we would have to enqueue at the position we use the modulo for. Yes. So when it's filled up here, so let me give an example now. This queue here is in my screen. This has 14 elements, right? So wrap around essentially means when you get to the end of the array, if you still have holes in the beginning, You store items in those holes rather than expanding the array. That's what I mean by wraparound. So in this case now, the array is technically the array is full. Like we can't add items to the end of this array. But we know that there are items at the beginning of this array that we want to use. So if you take what they call it now, if you take this, what you want to add, right, and you modulo it with the length of this array, you get back to 0. So in this case, we want to add the 14th element, right? We have 0 to 14, right? Yeah, so we want to add the 14th element. Or let me see. 0, 1, 2, 3, 4, 5, 6. So we want to add the 15th element. So if we modulo it with 15, so the array has 15 spaces. If we modulo the 15th element with the 15th space, we get 0. So we go back here. We want to add the 16th element. We modulo it with 15, we get 1. We want to add the 17th element. We modulo it with 15, we get 3. Like that. We get 2, sorry, like that. So the modulo helps you wrap around, essentially. Okay, so we would have to enqueue at the position we use the modulo for. Yes, that's correct. Okay, so depending on how you want to structure your queue, limited space versus unlimited space, you can use an array or linked list. Yes, you can use array or linked list to implement them however you want. And you can use an array to implement unlimited space as well, if you keep doubling the array when it's full. So either one can implement it. It's just that one is harder than the other. Yeah. Isioma, you have a question?
Okay, so please, this whole idea of implementing a stack or a queue using an array or a linked list, I'm a bit confused because I understand that these are like data structures in themselves, right? Or I mean, am I wrong? So why do I have to use an array? Like, I mean, the same way I create an array, or the same way I know that an array is a data structure, I might as well just create a stack and perform my operations on it. I mean, from Java and everything. So it's a bit, I don't really get it.
Okay, so 2 things. Arrays and linked lists are your basic data structures. Every other data structure you have are implemented using an array or a linked list. That's the first thing. So that's why we go about implementing it with arrays or linked lists, because every other data structure are implemented somehow using an array or a linked list, or a combination of both. But those are the fundamental data structures. Now, in terms of your language having a stack and a queue, yes, you can use your language to get a stack and a queue, but your language is implementing it using an array or a linked list under the hood. Yeah. But it's important you understand it so that it helps you understand data structures and algorithms and when you go to solve problems. Okay. So does that clarify your question?
Yeah, so okay, so in that case, like, I mean, I get the explanation you mean. In that case, now if I'm using my language, like a language like Java, that I believe it has stacks and queues, I don't have to go through the array routes. I should just go straight up to declare a stack or a queue.
Yes. Correct. Yes.
Thank you.
The reason why we are learning this is to really understand it and use it to solve problems. But generally, you don't implement a stack and a queue in production. No. People that are very good and have spent PhD thesis doing these things have implemented these things. So you are not really going to implement them. But it's good to understand how they work and when you use them. So let's see. Okay, so going back to our queue implementation, same thing. You can enqueue and dequeue in OR1, since you are adding from the front or the back, which are only dealing with the front or the back. Now, with the linked list, it's essentially similar to an array. It's just that in a linked list now, we add items to the tail of the linked list and we remove items from the head of the linked list. Same thing. It's even easier with a linked list because with a linked list, you can keep track of the tail. The only problem is that if you're using the single linked list, you can't remove from the tail. But since we can remove from the head, in this case, we don't care. So we just ask the tail remove from the head. So let's see how that works. And Q, the head and the tail are pointing to the same thing. And Q now, you see, we're adding to the tail. We add 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 to the tail. To the Q, we remove from the head. We remove from the head. Let me slow down the animation. So it's, we remove from the head. You see that? When we add to the tail. You see that? We're moving, adding to the tail, operating our pointers. There we have it. With the Q, we are moving from the head. So this is why people say using the linked list is better than an array because it's easier. But that doesn't necessarily mean it's more efficient. So this is essentially the same. I think this is clear, right? Is there any confusions around this? This should be pretty straightforward at this point because it's just adding and moving from one end. Okay. So I'll move forward now in that case. So what do we use queues for? We use queues for queuing items. Whenever I want to queue items, whenever I want to schedule jobs to run later. Like when you are programming or stuff, whenever you use here a queue, essentially is a queue. Like when you are using a queue to store items or to put items, you put items on a queue. Essentially, that's what it is. Breadth first search in trees and graphs. So this is a different one. Stacks are for depth first search, queues are for breadth first search. So these are very important things to understand. So question, does the fact that we might get to double the array not mean that using a linked list is more efficient? So doubling the array is O of 1 on an average. You only double the array a few times. If you add 1,024 elements, you only double the array about 10 times. So when you look at everything on an average, it's not really worse from a time complexity perspective. In terms of efficiency, what do you mean by efficiency? Like time complexity, the actual performance? I would argue, people have different opinions on this, but I would argue that implementing with an array is more efficient because the array allows you to cache things. Now, that depends on the size of what you're implementing. If you are storing integers, maybe not a big deal. If you are storing large objects, maybe an array will be more efficient, depending. Okay. So time complexities of a queue, constants for the main ones, fetch and remove from anywhere is still O of n. So this tells us that queues are not meant to be used for search operations or contains operations. There are better data structures that can do that. But those data structures will not give you access to the front and to the end. So you see the trade-offs coming in here. We talk about hash tables in future. Hash tables allow you to do search of contains in O of 1. But the items are not ordered. You don't know which one is in the front, you don't know which one is in the back. You don't have an order for how you inserted them. But an array could have unused empty memory. LinkedIn creates it when you need it. Yes. An array can have empty memory that is not used. Correct. Yes. That's very correct. And LinkedIn creates it when you need it. Yes. So if you are talking about it from a memory perspective, probably, maybe. But then if you are storing items, you are storing a lot of items, the overhead from the pointers of the linked list to begin to add up. Because the linked list has to store pointers, which usually adds up, depending on your so if it's a 64-bit system, pointer is usually 64 bits, which is 8 bytes. So if you are storing an integer of 2 bytes and you have a pointer of 8 bytes associated with it, so an integer of 4 bytes, the pointer of 8 bytes, you can see that the pointer is much more than what you're storing. That's where the trade-offs come into play. Yeah. So it's not really straightforward which one is better than the other. It depends on a lot of things. Yeah. So basically, synchronous methods utilize queues. So you can use queues to do synchronization in trading. Yes. You can use them to do synchronization in trading. Yeah. And the reason why you are using them is because you need a data structure that has first in, first out a first in, first out mechanism. That's why you need them. So later on, we'll talk about priority queues. And priority queues are also queues, but they allow you to give things priority. So some things have more priority than others. So you can use a queue. So there are different types of queues. The most basic type of queue is the first in, first out queue. Amazon SQS is usually a FIFO queue, yes. Yes. So now I'm going to talk about a variation. So are we okay with queues, please? It's very important to get this. Are we okay with queues? Perfect. Perfect. Okay. So now I'm going to talk about something called double-ended queues or DQs or decks. Now, let me just give you a caveat here. A deck is a doubly linked list. That is it. A deck is a doubly linked list. That is just, if you want to remember something about decks, I want to be able to understand it easily, is a doubly linked list. But what does a deck do? We've seen that stacks allow us to insert and remove items from one side of the queue. Queues allow us to insert from one side and remove from the other. Now, decks allow us to insert and remove from anywhere. So we can insert to the first. So insert first, insert to the beginning. Insert last, insert at the end. Remove first, remove from the beginning, remove last, remove from the end. So it's kind of like combining both of them. And these are other operations that are not really important. So now, the API, different languages call it different things, for instance. Like a deck in, so but basically a doubly linked list is a deck. So it can be used as FIFO or LIFO, depending on how you want to use it. It offers a lot of flexibility. It can be used as a stack and it can be used as a queue as well. You just need to modify the operations you do. So let's use the visualization of a DQ, how it works. So essentially, this is a DQ. Like I said, a DQ is just a doubly linked list. And doubly linked lists are good because we can access the front and the back, and we can remove from the front and the back. So, let me see. Oh, I need to. So that's essentially how it works. Let me see. Let me try dequeuing. So if I enqueue now, I can enqueue to the front, or I can enqueue. If I enqueue to the front, it adds to the front. You see that, and it updates the pointer. If I enqueue from the back, it adds to the back, and updates the pointer. If I dequeue from the front, it removes it from the front. If I dequeue from the back, it moves from the back. So essentially, this is a doubly linked list. Can I give a possible use case for a deck? Yes, in some problems, you need to access the front and the back. Sometimes you need to be able to move from the front and the back. Anytime you want to use that, that's when you need it. Now, some problems, a deck is very important. And sometimes some languages just offer you a deck. They don't even give you a stack or a queue, but you can modify a deck into a stack or a queue however you want it, removing from whatever side you want. Okay. So essentially, so that's what decks are. If you understand queues and stacks, decks are pretty easy. And the only way you can implement them efficiently is with a double linked list. And no, you can't use an array because you can't remove items. So you can remove items from the front of the array, but the problem is you can't insert items to the front of the array easily. I think it's possible if you double the array and copy it when you want to insert items to the front and keep items in the middle, you can make it work. You can't make it work if you start in the middle and expand. And when you hit either edge, you double. But typically people don't use an array to implement it. But that brings me back to my point. Almost every data structure can be implemented in any way. Like you can use an array to implement it, but it's hard, it's difficult. But if you really want high performance and your use case demands it, then it's possible. But most implementations just use a double linked list because it's easy. You just have to have your pointers to the head and the tail and expand the head of the tail, collapse the head of the tail. Super easy. So This is essentially what we've done with the double linked list. Operations are O of 1. Yeah, you can unshift, but it's expensive. These are the operations of the deck. Everything is O of 1. So note that you can use the deck as a stack. To use a deck as a stack, all I need to do is insert and remove from one side. So I'll call insert first as my pop, and remove first as my pop, and remove first as my pop. Yeah. So insert first as my push, remove first as my pop. Or for the stack, I can say insert last is push, remove last is pop. As far as it's still on the same side. But if I want to use a deck as a queue, I can say insert first, but then I have to remove last. Or I can insert last and remove first. So it depends. They're flexible. Just like stacks and queues, search and contains are very, very bad operations. You cannot search and contain, you cannot search a queue and you can't remove from anywhere in the queue. So where are decks used? Basically, anywhere a stack or queue can be used, since you can convert it to a stack or queue. Then sometimes we want the structure to behave as a stack, and sometimes we want it to behave as a queue, without having to use two data structures or copy from one to the other. Yep. So I think we have reached the end now, and we are actually out of time. I want to be very, very specific and stick to time here. So these were some problems I came up with that can help you practice. We can go over them if we still have bandwidth for it, but these are problems you can just use to practice and see applications of stacks and queues. Let's go over them. So let me go over the exercises first. Yeah, we'll do at least one. Let me go over the exercises first, then we can come back to it. For those that want to stay behind and go over it. But I want to finish the lecture by within 2 hours. So exercise, we can implement a stack. So this is what I would encourage you to do. Implement a stack using an array. Implement a stack using a linked list. Implement a queue using an array. Implement a queue using a linked list. Then implement a queue using a double linked list. As a stretch goal, implement a deck using an array as a stretch goal. But that's a bit difficult, but it's possible. So for exercises as well, the second exercise, the lead code, they have a learn card for stacks and queues. Just focus on the two I highlighted. Because in the lead code learn card, they talk about breadth first search and depth first search. But we've not talked about those, so you can skip those for now. And just focus on the queues and stacks themselves. For resources, same I shared last week, last 2 weeks, Groking coding interview patterns. They have for several languages. For me, this is the best resources. This is one of the best resources, the best resource you can get for learning patterns. But there's a catch, it's pricey. It needs a subscription for it. Maybe there are ways you can get it. Maybe it's possible, I don't know. Needs code is another one, but this is mainly in Python, and Group's Problem has video solutions. The visualizers are used to also, you can use them to kind of understand data structure. And I would say if you don't really, if you have difficulty implementing data structure yourself, now it's fine. You can, as you get more used to it, you can learn that, as long as you know how to use it. Because you can use data structures built into your language to use them. But it's good to know how they work on that. And some additional readings. Okay. So before we go into looking at problems, do we have any questions? Nancy, go for it.
Okay, hi. So good evening. Can you hear me?
Yeah, I can hear you. Go for it.
Okay, so I have 3 questions. So the first
Okay.
question is, okay, so I tried solving some lead code questions sometime last week. So I experienced some difficulties. The first one was how do you know? For some questions they will like you should have a time complexity of this and that. So like how do you know the particular solution that will give you this time complexity? Because most times I just go for the is it brute force? I don't know what you call it, but the easier one. But I don't know which one will give me O of n or all of n or whatever. And my second question is okay, don't answer it. Ask me second question.
Okay, so a couple of things here. If for the question on how to know the time complexity of your brute force solution, you just have to know how to learn how to analyze the algorithms well, and know, okay, this brute force solution is O of n squared, is O of n cubed, is O of this. Usually, it's usually n squared or greater. The second question, how do you know which time complexity is best for that solution? There are a couple of ways you can go about it. Some of it comes more with practicing questions. The other is by looking at what is the best possible solution you can have. Let me give an example. So if you have an array, right, and you are trying to do something on all the items on the array, you can't get something better than O of n. That's the first thing you need to understand. You can't get something better than O of n if you have to go through all the items in an array at least once. So generally, if you have something and you need to inspect all the items, then you can't do better than O of n for most array problems. But in some other cases, right, usually, unless the problem, right, specifies a very small input. So usually when you have a problem, they give you the input size. If they tell you the input size is 16, for instance, you know that you can use exponential or factorial or exponential or factorial for that. If they tell you that it's about 10 raised to power 5 or 10 raised to power 6, right? In that case, you are looking for something like O of n or O of n log n. The reason is this. Usually, when this code runs your problem, they run it on a container, right? They run your problems on a container. But the thing is, there's a certain number of operations that your computer can do. Usually it's about, I think, 10 raised to power 8 operations in a second. And they have a time lag of about, I think, 5 or 4 seconds for your test case to run. So based on that, if the input is like tending towards 10 raised to power 6, 10 raised to power 7, you know that, okay, I'm looking for something O of n log n. If they tell you it's about maybe 1,900, maybe an n squared might work. So you look at the input size they're giving you and try to see, okay, this is what they're looking for. But in an actual interview, for instance, if someone asks you that, you can tell your interviewer that this is the solution you come up with. They are trying to find a better one. But there's no hard answer that says, okay, this is where you must stop or this is where you can. Some problems, the best solution is O of n, some is O of n squared. Comes the combination of experience, look at the input sizes they give you, then you look at what is the fundamental thing you are doing. In an array, you can't do better than O of n. Usually in an array, if you have O of n squared, it's bad. Generally, you can do better than that. So if your brute force, for instance, gives you O of n squared, you know that definitely there's an easier solution. There's a better solution than that. If your brute force gives you like maybe factorial, maybe you can reduce it to n squared. You see the thing. So usually the brute force is easy to get, but trying to now see which one you want to use, it's a bit of an art too as well. So there's no real direct way to know really. Yeah. So the second question.
Okay, so the second question is, okay, so when solving a question, when do you know, like, how do you know the data structure to use? Okay, so this one now, I'm supposed to use linked list, I'm supposed to use an array for this, I'm supposed to use, so how do you know, like, the best data structure to use for a particular question?
So this is the thing, it depends on what the question is asking. Some questions, like they give you the problem in an array form, you already know that is an array. Some questions, although we've not reached that level yet where you have to formulate your data structure yourself. But in most of the questions, they give you like an array now, or they give you a linked list. For array linked list question, it's pretty straightforward. You have an array, do this. You have a linked list, do this. When you start getting to trees and graphs, right, then you start having to ask yourself, okay, should I use a stack? Should I use a queue? You see the thing. But most times, you don't use an array or a linked list directly to solve a problem. You usually use a stack or a queue directly. You use it as a stack or a queue most times. Unless the problem tells you it's a linked list. Then if the problem is a linked list and says, okay, find the middle element of a linked list, that's a linked list problem. For an array, they usually give you the inputs in an array form. then you're working on the array. Yeah, so that's mainly how you know. If you are talking of the algorithms to use, that comes with knowing the patterns, the problem solving patterns. And typically, there are multiple ways to solve problems. So as far as you can get a solution, and your solution is the same time complexity as what they have, don't worry too much if you solved it in a different way. Yeah.
Okay, so my last question is, can you explain the concept of greedy algorithms?
Of what?
Greedy algorithms.
Okay, so we'll talk about this in the algorithmic section, but greedy algorithm simply means, from the name, making the most optimal choice at a particular point in time. So with greedy algorithms, what essentially you try to do is you try to make the best choice you can find now, right? But the issue is the best choice might not lead to the best solution. That is the whole idea behind greedy algorithms. Let me try to think of an example. Okay, let me give an example. So let's say we have a boat and we have people lining up that want to enter the boat, right? And let's say we can take two people each, two people inside the boat, right? The boat has a certain capacity, right? How do we take people into the boat? We can only take two people into the boat, and the boat has a certain capacity. So thinking about it, what's the most efficient way we can do this? Usually, since you can take two people, right? You don't want to take two people that are light. You want to take, and you don't want to take two people that are heavy because they can't enter the boat. So typically you say, okay, let me take the heaviest person and let me find the lightest person if they can join. In that case, if you take the heaviest and the lightest continuously, you get the best solution to take those people across the river. But in that kind of case, you are taking the best, you are taking like the best you can find. So the best can mean anything. It can mean the largest, it can mean the smallest. Typically, it means either you're taking the largest or the smallest, or the one that has the shortest cost or the one that has the shortest path. Like when we talk about graphs, we talk about algorithms, like maybe directional algorithms, for instance. In that case, you are taking like the shortest path each time, the shortest path you can find. So greedy algorithms just essentially say, make the best decision you can make now. But the problem is that it doesn't always result in the right answer. But we'll talk more about this later. It requires you to understand recursion, understanding recursion trees, and solution spaces before you to really like to really make a lot of tie everything together. Yeah.
Okay, thank you.
Yeah. So any other question? We are done with the lecture now. If anybody wants to drop off or have any other things to do, please feel free. The recordings will be there if you want to continue later. Okay. So if we don't have any other questions, we'll go to problem solving. I'll try and do this, I'll try and explain the rationale of the problem and the idea behind it. I think that's very important to understand. So let's start with the first one, valid parentheses. So this is kind of like a classic problem. This is kind of like a classic problem. It's a very classic problem. And this is one of the core applications of the stack. So this question essentially is saying we have brackets. So if you think of a programming language now, maybe not Python, maybe Java, for instance, you usually use braces to denote things, or you use brackets, open and close brackets. When you are doing calculations, you use brackets to denote things. So in this case, it's saying, given a string that contains these characters, determine if this input string is valid. And an input string is valid if the open bracket must be closed by the same type of brackets. And the open bracket must be closed in the correct order. And every closed bracket has a corresponding open bracket of the same type. So this is kind of a classic application of a stack. Because if you look at a stack, you can nest things together. What do I mean? If you have, let me try and connect my writing pad to see if this would help. 1 second. So I might have to share my entire screen now, not just the window. so that we can see this. So I'm gonna, let me see if I can change it. So I'm gonna stop presenting and present my entire screen. Okay. Okay, now good. Okay, so essentially, right, it's telling us that how do we match parentheses here? So if I have, so let's take the base example. Open and close brackets. All right. Typically, there are multiple ways you can solve this. Right. If you use, but the classical way to solve is usually using a stack. So if you use a stack, when you see an open bracket, you push it to the stack. If you see a closed bracket, you pop it from the stack if it matches the open bracket. Now, where this is helpful is, let's say I have this. Now, if you have a stack like that, and you start from here and you go right, and you go this way. When you are here, right, if you push this to the stack, when you come to the next item here, you can also push this to the stack. Come to the next item and push it to the stack. Now, this is where it gets interesting. When you look at this item, you see if it matches what is on top of the stack. Now, because a stack stores things in last in first order, there's an ordering we can have where things are nested together. So in this case, because things are nested together, when you see this, when you see the reverse of a bracket, and you check the stack, if that is the most recent one, then you know it's fine. And then you can just pop it off the stack. Now this is what we have, and we are here. We see that this matches this, we pop this off the stack. And now we are here. This matches this. This is the opposite of this, and pop it off the stack. So you can see how a stack is very important for us when we are trying to match things together. So whenever you are trying to match things that are nested together, a stack is very useful. So that's actually the rationale behind this problem. Are we clear on this? Okay, Emmanuel, go for it.
Yeah, I'm clear on this question, but funny enough, I found out that you could solve this in a simpler way using regular expression, which was like one line of code. So my question is, do you think the regular expression kind of do something like this under the hood?
So regular expressions, they work in a very complicated way. Regular expression is a whole other ballgame. They work in a complicated way. They have things like, what they call it now, it's finite state machines. But the way they are really implemented, they're not implemented like this. Because with a regular expression, you can match a lot of things. You can match a single character, one or more characters, 0 or 1 characters, one or any character, a number. So it's complicated. It's not, it doesn't use a stack. It uses some finite state machine logic behind it to do that. Again, you can solve it in different ways. If you use a regular expression, in a real life situation, this might be how you want to solve it. But from an interview perspective, you want to show that you understand data structures. Yeah. And there are other ways you can solve this too. It's not just using this way too. You can do it, you can solve it with counting in a way, but it's essentially making what a stack would do. So for example, what I mean by counting is, let's say I create a count for this, I create a count for this, I create a count for this. Same thing. When I see this, I add 1. When I see this, I'll have 1. When I see this, I have 1. When I see the opposite, right, then I can remove it. But then I have to make sure it's in the same ordering I saw this, which is a bit more complicated, but it can be done. But so that's essentially it for this problem. Let me go over the code. Okay, so this is just what I did here. So essentially, this is Python. I don't really like to go over code like this because I know some people are not friends in Python. I'm more interested in you understanding the logic and then coding it up yourself in your language of choice. So essentially what I'm doing, I'm creating a mapping here. The mapping is just an efficient way so that I don't have to do too much if-else statements. This is a hash map, a hash table, hash map. We'll talk about that later. I think next week. We'll talk about it next week, but essentially the hash table, hash map. Then I'm creating a stack. A stack in Python is just a list. You can use a list as a stack in Python. So what I'm doing is I'm looping through all the elements in a string for char yes, and then I'm saying if my stack is not empty, and the top of my stack is equal to the inverse of what I have. So this mapping of gets me the reverse of what is on the stack. So, and if the reverse of what I have on the stack is what I have, based on this mapping, then I remove it. You see the thing? If it is not, I append it. That's essentially what I do. So at the end of the day, if I finish this operation, if my stack is not empty, then I know I don't have a solution. So how will my stack not be empty? My stack will not be empty. So if I have something like this, when I'm done with the whole operation, I have this, right? On this, I'll remove this. When I get here, I'll push this and I'll push this. So the stack will not be empty. If I have a modeled one like this, when I push this in, right? When I try to remove this, right? I won't be able to remove it. So I'll have to append it. And if I have this, there's no way my stack can never not be empty again. Are you naming the array stack? So a stack is, are you naming? Yes, I'm just naming a stack. Essentially, it's a list actually. That's just a list. I'm using a list in Python to represent a stack. So that's the point I was trying to make, that in terms of the actual data structures themselves, right? They are just interfaces that are defined to let you know what you need to do and what you are looking for. Now, in this case, I'm just using a list. I could also use a deck. I think I could use a deck for it. So in this case, let me just copy this solution here. And I think I've done. Just want to make sure I'm not missing anything here. Yeah. So again, when you are doing your own, I've done this program before, and I've what do you call it now? I've optimized the code. So I've troubleshooted any issues I got. When you are doing your own for the first time, if you submit it, it might not go immediately. I've done all that in the background, so we don't have to be struggling with it in class. So let me see. Okay, so why is it not zooming? Okay, so I could also use a deck here. If I say, I think I can use collections.deck. Yeah, and then instead of this, I have to say, instead of pop, is it pop? Append pop. Yeah, I think it's pop here. And then append, yeah. I think this should work. You notice I just changed this line here. So if I run it now, let me see if this works. Yep, same thing. So it doesn't really matter if I use a list. Now, the only difference is this one here is a linked list, because a deck is a linked list. And this is a list. Python version of a list. Or a Python version of an array. It says in an array, but under the hood, there's some things it does to make you store anything inside. I didn't change, I just changed one line and the same thing. And that's possible because the interfaces are the same. Yeah. Okay, so I think we can move on to the next problem. Any questions on this? Perfect. Let me move to the next problem. I'm going to try and breeze through them so that we can get through all of them. Number of recent calls. For some of them, I might not code them up. I might just explain it. The ones that are instance, I might explain them. So what they're saying here is you have a recent counter class, which counts the number of recent requests within a time frame. So now they are counting things within a time frame. Implement this class. Initialize the counter with 0 recent requests. Then when you ping, it adds a new request at time t, where t represents some time in milliseconds and returns the number of requests that has happened in the past x milliseconds, including the new request. Specifically, return the number of requests that have happened in the inclusive range of this. It is guaranteed that every code uses a strict value larger than the previous code. So this was what I was saying about the constraint in the previous case. Now, in this case, I see that the constraint, this is 10 raised to the power 9. So I know that I'm looking for a linear solution here, or a quadratic solution, a linear solution or a logarithmic solution. So a linear solution and better. It says at most 10 raised to the power 4 calls will be made to ping. Now, this tells me that so many calls will be made to ping. So I have to make this linear. I have to make it constant, because when you do n calls, everything will now be O of n. So I have to make these operations constant based on the constraints here. So if you look at this, right, this is essentially a sliding window problem. So if you visualize it, things are happening, right? And when their time does, they get removed from the window. If you have a window and the window is between this time and the other time, when things are happening and a recent item happens, you remove the other one from the window. What data structure does that signify to us that we should use? You can type in the chat. A queue, right? Exactly. So these are the ways you already know that, okay, I'm going to use a queue for this problem. That's just the first thing you think about. Okay, I'm going to use a queue. Then how do I use a queue? I need to add items to the queue. I need to remove items from the queue. So on what basis do items get added to the queue when a new request comes? On what basis does an item get removed from the queue when a request is old, when it doesn't satisfy this condition? Essentially, that is it. So that tells us that we also need to store the time of the previous call. Are we clear on this problem? Perfect. So let's look at the solution I have here. Good. So what am I doing? I'm creating a queue. Now, Python doesn't really have a queue per se. So I just use a deck for it. I mean, it has a queue. I think it has a queue. No, I take that back. It does have a queue. But I just use a deck for this. Essentially, it does have a queue, but the queue is more to do with concurrency. So it says here that this is the collections of queue, and it tells me that this is the time here. Now, when a ping occurs, I add the recent item to the queue. Now, what am I doing here? I'm saying that while the queue is not empty, and the item at the front of the queue is within the time frame I'm considering, is not within the time frame I'm considering. So it should be greater than t minus 3,000 seconds. But if it's less than that time frame, then I remove it from the queue. Then my result now is the number of items in the queue, because we are looking for the number of items at each time, and that is just the length of the queue, the size of the queue, of course. So this is essentially how it is. So just to make, so in this case now, we used a queue. Now, I could have also used a priority queue. A priority queue that is ordered by the time. We'll talk about priority queues later. But I'm just trying to make you understand that, like, looking at the problem and seeing which data structure to use is very important, because then you can now swap it out however you want. All right. So are we good? Are we good with this? Any questions? Perfect. Let's move to the next. Evaluate RPN. So essentially, A reverse Polish notation is kind of a way to do computations, really. It's a way that the computer can use to represent mathematical computations. So you are given an array in this case. So we know that we are working with an array since it's an array we got. That represents an arithmetic expression in reverse Polish notation. Evaluate the expression, returns an integer that represents the value of the expression. So these are the possible operators we have. Each operand might be an integer or another expression. The division between two integers always truncates to 0. There will not be any division by 0. So what they mean by truncate to 0 means that they are looking at integer division. So if you have 5 divided by 2, they take out the fractional part and it becomes 2. The input represents a valid arithmetic in reverse Polish notation, and the answer and all intermediate calculations can be represented. This is for Python, it's not important, but for C++ it might be important. So the reverse Polish notation is actually simple. What it does is it appends items to a stack. When you see an operation, you pop off the most recent 2 items from the stack, evaluate the operation, and push it back to the stack. So I think in this case, let me show my screen for an example. I think it would be clearer if I use an example. Let me. Okay. So let me come back to this screen here. Okay. So now we have 2, 1, plus 3, and times. So RPN, so this kind of question, reverse Polish notation is just something you just need to know. It's not really part of the problem. The problem is just to use a stack. So if I have a stack here now, right, and I start pushing items to the stack. So when I see a number, I push them to the stack, 2, 1. When you see a sign that is not a number, you pop up the most recent 2 items from the stack. In this case, 1 and 2. Do the operation 3 and push that back to the stack. Now we are here now, 3. We push 3 to the stack. When we see an operation here, we take up the last 2 in the stack, which is 3 plus 3, which is 6, and push it back to the stack. When we are done, the item at the base of the stack is our answer. So that's essentially how the RPM works. It might get complicated, but that's essentially what they are doing. When you see an operation, you take out the most recent 2 items from the stack and push them back. Do you have any questions on this? Okay. So the solution I have here is this. So the reason why I'm doing this is so this is just a map of the operations. So I have multiplication, subtraction, addition, subtraction, multiplication, division, and Python allows you to store functions as objects, essentially. So this is an add function. This is a subtraction function, multiplication function, and division function. So normally I'll have to have like an if else. I say, if it's addition, do this. If it's subtraction, do this. Or another function that does that mapping for me. But Python just allows you to do this easily. So I don't want it to be as if I'm advocating for Python, but again, I won't say learn the language for interviews. If you're already fluent in the language, keep using it. But if you need to learn one, learn Python. It will make your life easier. Tremendous. So I have a stack I'm using here now. So for trying tokens, I'm looking through all the stack, all what I have there. If my character is not one of these, then I append it to the stack. But then I'm appending it as an integer because, yeah. Else, I pop the top items in the stack. Then, what do I do now? I compute. So now what I'm doing here is I'm taking the operation here, which is addition. I'm feeding it into this map to get the function. So this is a function. This whole thing here is a function. And I'm calling the two, I'm passing these two as arguments to that function. I'm storing it back as an integer. Well, technically, I don't need this. I don't think I need this because they're already integers. Oh, so the reason is because of the division, the integer division. And then I return the item at the bottom of the stack. Okay. So yeah, I think, do we have any questions on this? So we could achieve this same thing here. What I have did here, you can achieve it here with if else or some other conditional, but it's just easier to do it this way. Any questions on this before we move on? Are people still there? Are we tired? Brains foggy? I know it's a lot. Okay, perfect. Okay. So what's the next one we have? Daily temperatures. So now these are more challenging questions. This says, okay, you have an array of integer temperatures that represent the daily temperatures. Return an array such that that array is the number of days you have to wait after that day to get the warmer temperature. If there's no future day that is possible, do this. So essentially here, what they are saying is, these are temperatures of days. And on each day, we want to know how many days you have to wait to get a hotter temperature. So let's say this is today. Today is 73 degrees. Tomorrow is 74 degrees. That means you have to wait 1 day, which is 1 year. On this day, we have to wait 1 day because the next day is hotter, which is 1. But on this day, we have to wait 4 days to get something bigger. Get something bigger than this, which is 76. That's why it's 4 days. On this, we have to wait 2 days. On this, we have to wait 1 day. On this, we just have to wait 1 day. Now on this one, this is 76. This is the end. There's nothing bigger. So there's nothing we can do here. And this one too, there's nothing bigger. That's what we can do here. So this is a pattern you might see common. This pattern is called, I think, monotonic stack. So essentially, it's when you have a stack or a queue, but you are storing them you are keeping only the items that are greater than others. So how do we solve this? What do we do to solve this? A brute force way will be, okay, every day, like if you start every day now, and you say, okay, for this day, when is the bigger one? This one. For this day, when is the bigger one? The next one. So you can do it with a brute force, but that will be n squared. And the problem here is, if you look at the constraints says 10 to the 5. So n squared is not going to pass this. That's the thing. So we need to make it n. But I know that because we have an array and we have to look through everything on the array to find something, I cannot get anything better than O of n. So I know that O of n is the best I can get. Now, O of n is what I can get. Now, how do I do that? How can I get the best of O of n? Any ideas? You can type in the chat if you don't want to talk. So how can I solve this problem? What are the ways I can solve this problem? Array I plus array I plus 1. I'm not sure I understand that. Okay. So the thing here is 2 pointers. Maybe 2 pointers might work. Maybe, but I'm not entirely sure how that will work. But it's possible it might work. But again, the point I'm trying to make here is not like to get a solution. There are many ways to solve a problem. You can brainstorm different ways. You don't understand the output. So for each given day, The output is telling you how many days you have to wait to get the bigger value. So on 73, which is the first item, you have to wait 1 to get a bigger value. But on this day, you need to wait 1, 2, 3, 4 to get a bigger value. Look through the array and check the difference between this minus this and store it in the new array results. Good. So if you look through the array and you check the difference between this and this, right? The problem is you are assuming. So that tells you the temperature difference between each successive day. Because if you take array I plus 1, that's the temperature of the next day, minus array of I, temperature of today. That gives you the difference in temperatures between each successive day. That doesn't give you the number of days you have to wait. You see the thing? So that approach doesn't work. I don't think it works. Maybe going by what you've explained here, or maybe you can clarify more. Okay. So the thing here is this type of problems, right? You're looking at it like, okay, you know that you have to go through everything once, right? But if I'm going through it once, right, I can go here and say, okay, I can ask the question on this day, what is the biggest temperature I can get? And I can go forward, right? But the problem is, let's say the biggest temperature I can get is here. It's 76. Let's say this was 79. I'll have to go through everything to get here. And then when I'm here, I have to go through all this. And then when I'm here, I have to go through all this. Do you see the problem? What if we go backward? If we say, okay, if we are here, right, we can know which one is lower. We can say, okay, from here we'll go backward. Right? I say, okay, 74.1, 75.1. But the problem is, if we are here, right, we can update everything less than this. And say, okay, loop through and update this. Loop through and update this. Loop through and update this. But the problem is that you could run into a situation where you have to keep updating everything because your temperatures are getting bigger each day. So if you have an increasing day, you have to update everything. You see the issue here. So the way to solve this kind of thing is, it might be tricky at first, but the thing is, if you know that at each day, if I know the number of temperatures that are lesser than me, I can update all of them. But I want to only update them when I see a bigger temperature. And when I see a bigger temperature, I don't care about what I have again. Can we use a hash map to update? I'm not entirely sure what you mean by using a hash map to update. Yeah, I'm not sure what you mean by using a hash map to update. So this kind of situation, now this is where it's good to know like some problem solving patterns. So the thing is, let me share mine. So the thing is, if I have okay. So the thing is, if I have like, let's see, so let's play with inputs. If I have 1, 2, 3, 4, 5, right? If I look backward like this, the problem is I have to update everything going back. But if you think about it, if I update 1 and I come to 2 and I update 1, do I really need to consider 1 again since I found the answer? No. So that's where a stack comes into play. So let me give the example here. Let's say we have 30, 40, 50, 60. Yeah. So if I have a stack here, when I see a temperature here, right, I want to check all the other temperatures behind me to see which of them I can update. There's nobody to update, so I push 30 here. Now, when 40 comes, 40 is greater than 30. So we definitely know that we are the solution to 30, and then we can update 30. We can update the position of 30 to be the difference. Oh, what is this? What happened? Oh, okay. Oh, okay. Okay. So can update the position of 30, right? To be the difference between, this is 0, 1, 2, 3, between the difference between their indices, basically. And then if we do that, we don't need 30 again here because we found the answer. We just have 40 left. Now if we come to 50, 50 is greater than 40. So we update it. 1, 1. We update that one and push 50 here. 60 is greater than 50. We update it 1 and push 60 here. Now 60 has nothing. We just have a 0. Now this is an easier example. Let me use a more contrived example. In the interest of time, I would have loved to like go through different approaches, but I will just try and quickly summarize it here. So the thing is, we have 73, 74, 75, 71, 69, what is it again? 72, 76, 73. So going by that approach, right? If you have this in the stack, when it's 73, we'll push 73 in here. When we get to 74, because 74 is better than 73, we remove 73, take it to use the difference between the two of them, which is 1, between their indices, which is 1, and then push 74. With 75, we do the same thing. We take the difference of their indices 1, and then here we push 75. Now, this is where things get interesting. With 71, do we have an answer there? It's less than 75, so we can't remove it. We just push it in here. With 69, it's not bigger than it. We'll just push it in here. With 72, 72 is bigger than 69, right? So now we can remove 69. But the problem is there are some other items here that we can't remove. So when we get to 72, we just remove 69 because we know that for 69, right, the difference is the 72 is bigger than 69. So we just take the difference between their indices, which is 1 in this case. I will remove 69. We push 72. No, again. So for 70, yeah, so for before we push 72, after removing 69, we see that 72 is also greater than 71. So we update the answer to be different between their indices here, which is 2. And then we check 72 and 75. It's less than 75, so we can't remove it, we push it in. So we found answers for these ones, 73, 74, 71, 69. But we've not found answers for the other two. Now, when we get to 76, right? 76 is interesting because 76 is greater than 72, right? So we can take out 72 and update it with the difference between their indices. 76 is also greater than 75, right? So we can now take out 75 and update it to be the difference between their indices now, which is 4. This minus this, which is 4. And we'll push 76. When we get to 73, 73 is less than 73. So we can remove it, we'll push 73. Now, when we are done, every item here has no solution. Just update the indices. I know it's a little bit confusing because this is more, I selected this problem because this is a more advanced application of stacks. But the thing is, to understand this, you need to know when to push, when to pop, and what conditions you need to push and to pop. So essentially, what we are doing is, when we get to an item, we check the stack if the items in the stack are less. If the items in the stack, okay, if the items in the stack are less, right, then we know that that is an answer to all the items in the stack that are less than it. So once we update the items in the stack that are less than it, and we have an answer to them, we remove them because we don't care about them again, and we push our new item to the stack. So if you take an edge case like this, so if you take an edge case now, that's and say, okay, if we have, say, 3, 2, 1, 5. So now, if we push 3 to the stack when we are here, when we get to 2, 2 is less than 3, we can't remove it because it's not a solution. If it was 4, we remove it because that is a value solution. 72 minus 69 is not 3. So we are not subtracting the values, we are subtracting their indices. They are indices in the array, not the actual values. The actual values are the temperatures, the indices are the days. So we have 3 here. When we come here, 2 is not greater than 3. So we can't remove it because it's not a solution to 3. So we need to put it in here. Essentially, anything you have in the stack does not have a solution, does not have an answer. When we get to 1, 1 is not greater than 2. So basically, the elements lesser than the highest temperatures would be equated to 0. No. Do you mean greater than the highest temperatures? I'm not sure I get the question. So for 1 is less than this, so we have to put it there. It's not greater than it. If it's not greater than it, we have to put it. If it's equal to, we have to put it because it has to be strictly greater than. Now, but when we get to 5, something interesting happens. 5 is greater than 1. So definitely that 5 is a solution to 1. So we update it with the difference between the indices. So again, I'm putting it here to store the values, but actually I should be storing the indices. But storing the values makes it easier for us to get through. Because if you store the indices from indices, you can get the values as well. So from here now, we subtract the indices of this and this, which gives us 1 for this solution here. And then we take it off since you have a solution. We look at the next element here. It's bigger. So we subtract the indices here, which is 2. We take it out because we have a solution. We look at this one now. We subtract this minus this, which is 3. And then we take it out because we have a solution. And then when we are done, we push 5. And at the end of the array, 5 doesn't have a solution, we put 0. I know this example is a bit involved, but I just wanted to show the application of start, pushing, popping, and conditioning. In the temperature question, there was no other index that contains element higher than 76. Hence, you return 0. Yes, correct. Yeah, correct, yeah. So it's for the implementation of that, I did something here. Especially this implementation here. I have a stack. Now I'm creating an array to store the results. This result is just storing 0. So by default, I'm giving it 0 unless I update it. It's a way to optimize the solution so that I don't have to check the stack and update the stack at the end. And update the items that are in the stack with 0 at the end. So I look through the temperatures and the indices. So enumerate in Python just gives you instead of giving you just the index, it gives you the index and the value. So you can do that. You can use a tuple. But again, if you keep the index and the value, so someone is asking, I think I understand, but to keep the index along with the value, you can use a tuple. Yes. But if you have the index, you can get the value. So you don't need to store both. That's the optimization. But yeah, that would work. So what do we do again? Essentially what I said, while we have the stack, if the temperature on top of the stack, so stack -1 in Python just means the last element, instead of doing len of stack -1. If the temperature on top of the stack is less than my temperature, the current temperature we are looking at, right? We'll remove that item from the stack, the index of that item. So we are storing the indices. We set the results at that index to be the difference between our indices, between this current index and the index of the item we remove. Then we append this index to the stack. That's essentially the algorithm. So it runs through. Then at the end of the whole thing, the stack will have some items that we didn't update. Ideally, we should update them. But because the result was set to 0 initially, we don't need to update them. Just an optimization. A bit involved, I know. But do we have any questions on this? Thumbs up, good. Thumbs down, not good. Oh, I can see a lot of thumbs up are coming somehow. So this type of problems are, again, this is not an easy problem. This is not an easy problem. But I didn't want to just be solving easy questions. I didn't want to just, I wanted to also show like some difficult questions as well to give like a realistic view of how problems are. But again, if you can't solve this initially, it's fine. But it's just to understand that the applications of Stack and get you thinking about how you can use Stack. Isolations included? No, they are not included. So what I would do is I would share them in a GitHub. I would share them in a GitHub page. I could include them in the slides too. Okay, what I would do is I will include this Jupyter notebook in the resources that will be shared. This entire Jupyter notebook. Yeah. So let's see. Do we have bandwidth for more questions? Or do we just stop? I see we are getting tired. Stack the give headache. So it takes time to get it. If you just learned it now, it's a bit challenging. Yeah, Emmanuel, go for it.
Yeah, sorry, please. I'm from a language that uses something like Java. I'm from that programming language, but I saw something that when you're trying to get the length, you use what they call it, length. It looks like a function. My question is it looping to get, like, is it like looping then trying to get the length of the array? But in programming language like what they call it, like that language now, I think it gets the length and each time you add something to the array. So my question is, how is it that for each time you call the length function, that's an O of n operation?
Very good question. So ideally, if you look at it, each time we call the length option, it should be an O of n. But what most languages do is that they store the length of the array as a variable and they update it as they go. Yeah.
That programming language stores it, but I'm asking in particular of Python. Like, does it stores it? Because it looks like I'm calling a function, like the length function.
Oh, I see. So Python does a lot of things to make things easy. But when you call the length function on Python, essentially it accesses the variable and returns it back to you.
Sorry, come again.
It accesses the variable storing the length and returns it back to you. It's not it doesn't do the computation each time. It stores what the length it has saved is.
Okay. That's nice.
Python is funny. It makes a lot of things easy and it abstracts a lot of things. Essentially, if you call the length of anything on the sequence, it doesn't go and get the length at that point in time. It just gives you what the length is directly. Yeah. Okay. Do we have bandwidth for more, or we should call it a day? Thumbs up, thumbs down. Let's take a poll. Okay. I'm seeing more thumbs up, so I guess I'll just go through the last two examples briefly. Okay. So for the main stack, I think I can skip this one. No, let me go over the last one. Let me go over the last one. I think this is a medium question. Let me go over a hard problem just to see. Now, word of caution, this problem is a hard problem. It's not an easy problem. So it might be a little bit, but this is a hard problem with a queue. So essentially it's saying you are given an array of integers and there's a sliding window of size k, which is moving from the very left of the array to the right. You can only see k numbers in the window. Each time the sliding window moves right by one position, return the max of the sliding window. So what they are saying is each time we have these sliding windows going across, and we want to return the maximum in the sliding window each time. Now, the brute force solution is just to return the maximum. Go through each of them and return the maximum each time. That's the brute force solution. But that will give us n squared. And what are the constraints? Oh, we need an O of n solution. So again, this is a difficult problem, and solving it requires having some insight into how stacks and queues work. Yes, go for it, Emmanuel.
Yeah, sorry. It's like you're doing some magic. The way you're looking at the constraint and the way you could determine, like, okay, the solution they want us to do is O of n or O of something. How do you do that? Like, I don't understand how you just look at the constraint and okay, this solution, the best outcome will be of O of n or something. I
Okay,
don't
cool.
understand.
So now, okay, cool. So look at what they are giving us. They give us nums. Nums is an array, right? They give us key. They give us the output. We don't care about the output. We just care about the inputs. Now they are telling us that the length of that array is 10 to the 5. That's like 100,000 elements, right? And k can range to the length. So k can also be 10 to the 5 in the worst case. Now the thing is, if you have this type of input, right? Typically, you are looking for O of n or O of n log n, but n squared will not pass this type of case. If you have like 100, 1,000, or anything less than 1,000, you can try using n squared. If you have like 10, 20, 30, very few, then you can use brute force. You can use a combinatorial enumeration, factorial power. What do you call it now? You can use factorial or exponential. So I do that from the input here. So if I see that this is like 100 million or 10 to the 9 or 10 to the, or if they say 20 million, then I know it has to be constant. Again, is the reason why I'm able to do that is just because I've practiced with enough questions to know like how the constraints are determined. That's the thing. But typically, like in an interview, you can also determine from the type of the problem. So from the type of the problem, you can know what you're expecting. In this case now, I'm looking for the maximum of the sliding window, right? I can't get anything better than over here. Like it can, maybe it's worse, but it can be better. So I know I cannot get log n. I know I cannot get constant because each time in the sliding window, I need the maximum. And to get the maximum, I need to look at all the items at least once. So if I have to look at all the items at least once to get the maximum of everything in the collection, then I can't get anything less than looking at all the items, which is over. Now, if I'm looking at the items at least once, right, and I'm just comparing, then I can get over them. So the first thing that will come to my mind is, how can I do this looking at each item once? Now, if I go through the loop, like if k is 3, I can just loop through three times, right, and get an answer. Like I can just loop through, I can just loop through with an element of 3 each time and get the max and return it. That would work. But the problem is that's going to give me O of n by k, n times k, right? And if you look at the constraints, they said k can be up to norms of length. So if norms of length is n, that means k can be n. So that will give us n squared. See the problem? So, and I know from the constraints that this already will not pass because this constraint is large. It's either linear or linearitmic, n or n log n. So I have to find an optimal solution here to give me either linear or linearitmic. So again, if it's an actual interview again, like usually, I have to notice in interviews or when people are doing things like this, when you are doing this code, you're just looking at the problem yourself. In an interview, you'll be communicating with somebody and you'll be having a back and forth on your thought process. And if they see that you are stuck, they can give you hints. So what you need to understand is most of these code problems that are hard, if you get the right hint, it can become easy. It can become medium, sorry. That's the thing. But on this code, you're just looking at it, you don't really have anybody you're rubbing ideas back and forth. But in a real interview, you'll be rubbing ideas back and forth to somebody. So they will give you hints and you should be taking the hints because those hints are meant to direct you somewhere. So in this kind of case now, how do we solve this kind of problem? Like, I know that definitely this is a queue, and I need to maintain the largest in the queue at any point in time. But how do I do that? I mean, okay, and I get like, there's something called the priority queue, like a heap, which I think we can use, which we should be able to use here too. but we can't. Well, I won't use that because you've not done it. How to know the time complexity? So, in terms of the time complexity, you look at what they're asking you to do. They're asking you to do something, and they're saying you need to find this, and to do that thing, you look at what is the minimum amount of work I need to do to get that thing. So, if now you are looking for the maximum, the sliding window maximum, it means for you to find the maximum of them, you need to look at all these elements at least once to find the maximum. You can't, if you don't look at all the elements, you cannot find the maximum in the collection of elements. So that alone tells you that you cannot do better than all of them. I think that's what they call the best conceivable case. Like just by elimination, like by thinking about it, I can't do better than all of them. There's nothing I can do with log n here because there's no such thing. And definitely cannot be constant because I have to look at multiple elements. Yeah. So that's how I know. So in this type of problem, right? Usually this is something you might have to try different approaches to be able to get. But the key here is for every window, we need the maximum item. So how do we store the maximum item? Let me share my screen. Okay, so I'm just erasing. Okay. So now let's look at this now. If we have, let's say we have 1, 2, 3. And let's say we are looking at it 3, 3, 3. How do we find the maximum? So remember, this is a queue. Items live in this order, right? These are the items that leave the queue first. And these are the items that enter the queue. Now, so if I look at this item and I store it in a queue here, so if I have a queue here, for instance, can be a queue, can be a stack, I don't know. But when I see this item here, the largest item is the only item I saw, which is 1. Now, when I see 2, right, what does that tell me? 2 is the largest item, right? So I can store 2 here. But the problem is 1 is going to leave before 2. So if 1 is going to leave the queue before 2, I could as well just take out 1 and forget about it. Because as long as 2 is in this lower queue here, as long as 2 is in this queue, 2 is going to be bigger. And since 2 is bigger than 1, since 2 is bigger than 1, I don't need to store 1 here. So essentially, the item here is the biggest. It's the biggest I can find. So this is going from big to small, smallest. So when I come to 3, right? 3 is greater than 2. But because 2 is going to leave the queue before 3, as long as 3 is here, I don't need 2. So I can take out 2 and just store 3 here. So 3 is the biggest here, which is correct. Now, when I get to 4, I need to take out 1 out of the queue. So if I take 1 and I compare it to 3, I see that 1 is not equal to 3. So I just ignore it. But 4 is bigger than 3. So I take it out and I put 4 here. And the same thing for 5. So let me take a more contrived example now, just to illustrate some things. So let's take the example here. So we have 1, we have 3, we have -1, -3, 5, 3, 6, 7. So the idea here is to have a queue that stores the largest. So when I get to 1, 1 is the only thing I've seen. If I get to 3, right? 3 now is larger than 1. And because 3 is going to leave the 1 is going to leave the queue before 3, then I can just remove this and put 3. Pop it out and put 3. When I get to -1, now things get interesting. -1 could be the largest at some point if 3 leaves the queue, right? So I need to store -1 after 3. What of -3? can you recap so that I can follow with you? So this question is a bit, I would say it's a bit challenging, and it might be something you might need to like sit back and really think about it to come up with this answer. Because coming up with this answer directly is not, it's not easy. Unless you've been really solving questions where you're really good at it. So essentially, we are trying to find an efficient way to store the maximum in the queue at any point in time. Yeah. So -3 here could be the largest in the queue at some point. So we need to store it. We can't ignore it. Now, when we get to 5, remember the queue is moving like this. Now, when we get to 5, right? 5 is greater than all these elements in the queue. So as long as 5 is in the queue, all these elements are not useful because it's bigger than all of them. It's going to be bigger than all of them. So you can just clear everything here and put 5 and so on. So I'll just go through the solution here. No, it's a bit, that may be challenging to understand, but this is the solution here basically. So I'll try and explain it. This is the queue I'm using. This is the queue that stores the maximum. And this is the result. So this first part is just the first key element. But essentially what I'm doing is, while there's the queue, and what is in the queue is less than the current number, remove what is in the queue, then append the current number, and then update the result. So we do this same thing here. The only difference is we check if the number we are taking out of the queue is what is the current max, and then we just remove it. Yeah. I know I'll get a lot of thumbs down for this. Thumbs up, thumbs down. People are scared to put thumbs down. Put thumbs down if you want to put thumbs down. There's no, I know it's challenging, but you might need to take some time to really go through it. And in the interest of time, I don't really have time to really like sit down and explain it very well. So yeah, I think we call it a day at this point. Maybe we can move the conversation up to Slack or something. But again, this question is a hard question. You're not expected to solve this question like on your own without hints. Generally. Yeah, you can go to the instruction and ask question on Slack. Yes. Maybe that would be better. Yeah. Like, also find some videos that also explain how the intuition behind solving this. But this question and this question here, they are kind of two sides of the same coin. The patterns are similar in that you're trying to store the min or max, and you are removing for the min or max. Okay, I think we've overstayed our time, and at this point, I'd like to end it. Thanks everybody for sticking this far. Yeah, over to the organizers.
Yeah, thank you so much. Like, it was really an educative session. We really appreciate you for this time. And so I hope you guys go back to this video. We are going to upload the video on our YouTube and also share it with everyone after this call. And that's possible maybe tomorrow. Tomorrow, you guys are going to get that tomorrow. So we advise you guys to please fill the feedback form that's in the comment section now. Please, guys, in the chat box, please, guys, let's fill that, and see you guys on the next call. Thank you so much for your time today, and see you guys next week.
All right, thanks everyone. Bye.
Yeah, bye.